Hello, good morning.
Good morning, Dr. Hanif. Good morning.
Good morning, Dr. Lucy.
Thank you for coming today.
Yeah, thank you. Thank you for inviting me.
Yeah. How are you today, Dr. Hanif? I hope you are
Alhamdulillah,
healthy.
it's good. Yeah,
Alhamdulillah.
Alhamdulillah, yeah.
We will start our meeting maybe 5 minutes later.
Okay. So how many presentations do we have this morning?
5. Totally it's 5. 5 presenters.
And I'm presenting the first one at 9.
Third presenter. So the first,
okay.
Yes, the first is Professor Toshiharu Enomai from University of Tsukuba, and then the next presenter is Professor Muhammad Aziz from Institut, University of Tokyo, Japan, and the next presenter is yours. Yeah.
Okay, that's great. Thank you very much.
Okay. You are welcome. Enjoy this meeting, Dr. Hanif. Enjoy this meeting today.
All right.
Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Good morning, everyone. First of all, we are delighted to welcome you to our last world-class professor series about future trends in renewable energy and enabling technologies for sustainable development. The Honorable Rector of Institut Teknologi Kalimantan, Professor Insinyur Budi Santosa, MS PhD, the Honorable Professor Toshiharu Enomai
Recording
from
in progress.
University of Tsukuba, Associate Professor Muhammad Aziz from Institute of Industrial Science, University of Tokyo, Japan, Dr. Abdul Hanif Mahadi, Deputy Director at Center for Advanced Material and Energy Sciences, University Brunei Darussalam, Dr. Eng Atip Amrullah STMN from Department of Mechanical Engineering, Universitas Lambung Mangkurat, and Dr. Eng Panji Parawisuda STMT from the New and Renewable Energy Research Center, Institut Teknologi Bandung. The Honorable Dr. Eng Luciarnawati STMSC as the World Class Professor Awardee, and all of our participants for today's event. I am Azmia Rizka Nafisa, Lecturer of Institut Teknologi Kalimantan. As today MC, super excited to host the event for today. It is such a great opportunity for us to interact and connect through this virtual event and have an amazing talk and discussion about renewable energy. Thank you for spending your weekend and joining our virtual webinar with us. This event is the fifth series of World Class Professor Program financed by Indonesian Ministry of Education, Research and Technology in collaboration with LPDP. In this webinar, we will discuss some topics about energy, such as management of renewable energy to ensure national security, challenges and opportunities for Indonesia bioenergy, utilizing biomass and household waste potential for bioenergy, and other interesting topics. Before we start to the main event, we will hear an opening remark from Rector of Institut Teknologi Kalimantan, Professor Insinyur Budi Santosa, MS PhD. To Professor Budi, time is yours.
Okay, thank you. Good morning, ladies and gentlemen. Thank you for coming in this webcast professor webinar series with the topic of future trends in renewable energy and enabling technology for sustainable development. For the audience, thank you also for you all for coming or joining in this webinar. I hope from this webinar we can share idea, thoughts or insight how to develop renewable energy, especially maybe for the new capital city in Sepaku. I think we hope that we can develop some renewable energy to support this new capital city of Indonesia. Thank you for Dr. Lucy for obtaining this scheme of world-class professor finance, yeah, because of your participation and maybe one of other faculty that obtained this scheme from LBDP. So we can develop some academic and scientific activities in ITK. Although our doctoral lecturer is only 6, yeah, but your participation in this scheme for this world-class professor is very important for ITK. We can show to other maybe neighbor around ITK that even we still small, but we can take a very good step in developing our academic atmosphere in Kalimantan Timur. Yeah, I hope that some speakers will give new insight and idea so we can discuss the most recent development in renewable energy and technology that support sustainable development. Thank you for all participants. I hope that this event will go well and you can take some advantages from this event. Thank you.
Okay, thank you, Professor Budi. And the next one is greeting from the world class Professor Wardi, Dr. Eng Lucy Ernawati, ST MSc. To Dr. Lucy, time is yours.
Okay. Thank you very much, Ibu Asmia, as our master ceremony today, and the honorable speaker, Professor Budi Santosa, as rector of Institut Teknologi Kalimantan for opening speech this morning. And thank you very much for honorable speakers today, Professor Aziz, and then Dr. Abdul Hanif, Dr. Panji Prawisuda, and Dr. Afif Amrullah for meeting today, and also all the participants for coming today's seminar. Let us thanks to God for give us the healthy times and air for us that we can gather in this occasion. And hopefully this meeting will be beneficial for us, especially to discuss about renewable energy, and we can connect each other, make a network, and also a research collaboration as well. And then also, I hope this seminar will be a great opportunity for us, and can share our knowledge about renewable energy. Okay, I hope all the participants will enjoy for 2 hours letters, 3 hours letters in this seminar. And thank you very much for attending this seminar, and hopefully you will enjoy for this meeting. Thank you very much. Back to the master ceremony today, Dr. Asmia. Thank you very much.
Thank you, Dr. Lucy. The next presentation and discussion session will be led by Dr. Musharofah, SPDMSI from Institut Teknologi Kalimantan. But before I give the chance to Dr. Musharofah to start leading the session, let's take a picture together. To all of the participants, please turn on your camera and please use our virtual background so we can have a great picture together. Okay, now I will take the picture of the first page in 3, 2, 1. And then the second page, 3, 2, 1. And the last one for the third page, 3, 2, 1. Okay, thank you. Now we are going to the main session. I'll give the chance to Dr. Musharofah to lead the session. Dr. Musharofah, time is yours.
Thank you, Bu Asmia. Is it my sound is clear?
Yes.
Yeah. Good morning, ladies and gentlemen. Thank you all for finding time and visiting this webinar. I'm Musharofah, a lecturer in Institut Teknologi Kalimantan, and today I will be your moderator for this webinar. It's great that we can all meet today to explore the topic, future trends in renewable energy and enabling technologies for sustainable development. We hope that this meeting will encourage our knowledge about how to optimizing the management of renewable energy to ensure national security, and then about challenges, opportunities for development of bioenergy, biomass, clean energy technology, and biofuels. And then we hopefully can get inspired how to improve and utilize our locally available resources. And then, first of all, I would like to introduce to you our speakers at today's webinar. The first one, we will have a special guest from Department of Life Science and Environmental Engineering, University of Tsukuba, Japan, Professor Toshiharu Enomai. And then we will have 4 keynote speakers. The first one is Associate Professor Muhammad Aziz from Institute of Industrial Science, University of Tokyo, Japan. And then the second one, we have Dr. Abdul Hanif Mahdi. He is Deputy Director at Center for Advanced Material and Energy Sciences, University Brunei Darussalam. And then the third speaker, we have Dr. Eng Apip Amullah from Department of Mechanical Engineering, Universitas Lambung Mangkurat. And the last one, we will have Dr. Eng Panji Prawisuda from New and Renewable Energy Research Center, Institut Teknologi Bandung. Okay, ladies and gentlemen, thank you for all speakers. We appreciate your being with us today. Before we get started, I'd like to go over a few items to all participants. Today, we will have 30 minutes presentation from each speakers. And then a question and answer session will be held after the all presentation. I advise participants to turn off the mic when the speaker presents. You have the opportunity to submit text questions to our speakers by typing them into the chat box. And then you may send in your question at any time during the presentation. And I will collect this and address them during the Q&A session. And also you are welcome to ask questions directly to our speakers during the Q&A session by click the raise hand button, and I will let you to turn your mic on and you can deliver your question. Okay, ladies and gentlemen, without waiting any longer, let's please welcome our first speaker, guest speaker, Professor Enomai. Time is yours.
Okay, thank you for kind introduction. My name is Toshiharu Enomai from University of Tsukuba, Japan. Okay, today's topic is first I'd like to share my screen. Okay, can you see my slide?
Yes, Professor.
Okay.
Yeah, we can see, Sensei.
Hey, thank you. Okay, today's topic, my topic is electricity generation from paper vibration by electrostatic induction. Okay, first of all, I'd like to introduce the paper production in Japan. So, paper industry uses a lot of biomass like wood and some other plants to make paper. And that's why very closely related to the biomass industry. And in this figure shows the paper board and the paper production in Japan. And the curve in pink, in purple, shows the production of paper and the transition of the production from 1916 to 2020, last year. And the curve in yellow shows the paper board production. Paper board is a very thick paper, like corrugated cardboard for a corrugated board, and some other packaging. Okay, and so far, compare when we compare between paper and the paperboard, so paper has been always had a higher production than a paperboard. So that's because information is very important. That's why advertisement and other brochures of products are printed on paper, coated paper with very high print quality. And the production of paper also increased and always higher than the paperboard. But now last year, if you look at the here, look at the production in 2020. So the production of paperboard, mainly for packaging, it was higher than that of paper. That's why our focus, or paper industry focus, now moves from the information paper to packaging paper. Okay. And in biomass industry, our the utilization of biomass. So energy sources are always three kinds. Has categorized three kinds. The first one is the solid fuel. So this is the other solid fuel pellets like this, as in this picture. In this picture is used. So this is the diffused paper and the plastic fuel. Plastic is not good for environment because it emits a carbon dioxide and not renewable energy. But actually, plastic has a high energy for energy production. That's why RPF is used. Now, the second one is the liquid fuel. This is the bioethanol, for example. Oh, I'm sorry. Okay, and the liquid fuel is bioethanol. And gas also used for energy source. So by thermal decomposition of biomass, and hydrogen gas and carbon oxide gas are obtained. It is used for power generation through gas engine. And the methane gas also available. This is from garbage fermentation. Okay, so out of these energy source, so okay, I'll skip this one. Okay, so but now promotion of a cascade utilization is very important. So for example, this pellet can be produced for waste paper. Okay. Waste paper is several times recycled, but after that, all the fibers becomes very small particles. Those particles fines are not well utilized for paper making. That's why it can be used for energy production. Okay, and bioethanol is very important, but usually from wood, bioethanol is used. But no, and after decomposed to glucose unit. Okay, this is the source of bioethanol. But wood is very useful for paper making. And then after that, so from waste of paper, so glucose is produced and then converted to bioethanol by fermentation. Okay, and this table shows the efficiency of energy. So for example, this is a combustion heat per gram of material. For example, hydrogen gas. So now hydrogen battery is becoming more and more important because hydrogen gas have a high power, And this value is a combustion heat and 141.8 kilojoule per gram. So per gram, so hydrogen gas has a lot of energy. And also methane gas also high power, but much lower than hydrogen. And how about, and the bioethanol is sometimes used as a liquid fuel, but this is the which one? This is ethanol. But ethanol has a very low combustion heat, 29.7 per gram. That's why efficiency is not high. Okay, so about 10 years ago, bioethanol production was very popular, the very important topic for renewable energy. But now, very low combustion heat is a demerit, and many projects for bioethanol production is already stopped. Okay. And this is energy consumption, composition of a paper making industry. So paper making industry use a lot of energy for paper production, for drying and pulping and so on. And this is a composition of energy source for paper making. And half of them are fossil energy from coal or heavy oil or gas or purchased electricity from a power company. But the other half is about 43.5%. If we, so this biomass waste, so this is more than 50%. And the most representative energy source is the black liquor. This occupies 1/3 of the total energy required for paper production. The black liquor is after pulping, so the waste liquid is emitted. But this is called black liquor. This black liquor contains lignin. So about 25 to 30% of the component is lignin. And this can be used as a energy source because it contains a lot of organic materials. Okay, and so the total energy of black liquor is 33.8%. This is about 1/3 of the total energy required. And this is all comes from biomass. That's why after burning, so carbon dioxide gas is emitted, but this carbon dioxide gas is not different from petroleum or coals. That's why this is the renewable energy. Okay, so this is how a black liquor is emitted from a pulping process, and wood chips are pulped or digested using alkaline chemicals and at high temperature and high pressure. And the pulp fibers are extracted, and the other residuals are called black liquor. And in recovery boiler, this black liquor is dried and burned, combusted, and to get heat and electricity. This is utilized. This is utilized for bioenergy. Okay. And during a combustion, some chemicals are recovered. Okay. And if you put some supplement of sodium sulfate, so this is the only supplement after one cycle of pulping. And then other chemicals are all recovered from the black liquor after burning, and it becomes green liquor and also finally a white liquor. And this contains sodium sulfide and sodium hydroxide. This is required for pulping as chemicals. And these and these chemicals are recovered from the black liquor. Okay, and then new wood chips are added for pulping in the next cycle. So that's why this cycle has a continuous forever by adding only a little supplemental sodium sulfate. Okay, so now I overview the situation of the energy source in pulp and the paper industry. Okay, now I talk about a little bit more a shift to my own research. My research, my laboratory is paper device and eco-friendly materials. And today I talk about electricity generation from paper vibration. Okay, this topic was researched by Effie Octavia. Okay, so first I'd like to show the movie. Okay. A few years ago, this poster was put up in the Shinjuku station. Sorry, no sound. Okay, can we? Oh, I'm sorry. Oh, again. Oh, which one? Again. I think you can hear the sound. This is a poster, a movable, very active poster of a museum exhibition of ukiyo-e. And in this poster, so some plastic sheets are moving around like this. Okay, this is very attractive and very good advertisement for art exhibition. Okay, so this poster is activated by electricity, but if it is sourced from energy harvesting, so it is very useful because no cost is required for activating the poster. So this figure shows energy harvesting. So around us, there are many types of dissipated energy. For example, light. Oh, this is mainly from sunlight. And heat from brakes of vehicles, and also directly from human body. And the radio wave also has energy. And vibration, like bridge and motor cars has always vibrating, and this vibration is also a kind of energy. And if utilizing this harvest energy around us, so we can create a self-powered paper device. So by energy harvesting from noise, voice, and sound, so this energy source always vibrating paper. And if we can get this vibration energy from that paper, we can make an on-site electronic power supply. Okay, for example, if we illuminating paper, so with inorganic electroluminescence. So if we sound vibrating paper of this type of illuminating paper, we can get the lighting illumination from this device, okay, and some others. And a principle of electrostatic induction. This paper vibration energy can be converted to electricity using the electrostatic induction. And if you put the static electrode here, two electrodes, and one side is a static, and this is the attached to the electrode. Electrode has a material with a permanent polarized material with always charged. And on the other side, so this is a moving electrode, and by vibration induced by noise, for example, this moving electrode, this electrode is always moving. And if this moving electrode comes to the surface, near the surface of this electrode, the charge is a positive charge go in this direction. But when it's moving away from the electrode this way, the positive charge goes back. And during the vibration, this back and forth action of electrons make electricity. Okay, so we try to make a prototype generator using a hand fabrication, and check the if this electricity produced can light a LED. Okay. First, we fabricated this power generator, and this is the moving part, and this is the fixed part. So usually, this we take this moving part down to the over this fixed part, but not in contact. And using hand stroke, this moving part is moved. And this moving part has a electrode here. This is a white material, like Teflon. And this moving part is has charged at the bottom of this sheet. And this is a negatively charged here. Okay. And when during the hand stroke, this part moves to over here. Okay, that's why this part comes over here, and this negatively charged part attracts a positive charge like this. But if you move over here, negative charge is from here to here moves over here, and this changing is repeated. So this is a electricity flow. Okay, using this system, we measure the generated voltage between two electrodes here. So this is not in contact, the different independent two electrodes. And during stroke, so generated voltage is generated like this. And for example, between the moving part, at the distance between the moving part and the static part, a smaller, shorter than here, to 1 millimeter gap, and this generated the higher voltage. Okay, and also the same. This is after Fourier transform, and it has some peak. So this depends on the frequency of hand stroke, and also the interval of the the electrode shape. Okay, second one is a LED lighting dial. Wearing hand straw. Like this. Okay, I'll skip it. Okay, so successfully light LED was lit. Okay, and then we measured how a paper vibrates during sound is emitted from the speaker. So we put the wooden ball here, and also we put the this is our paper, two papers here. Oh, okay, the same. So speaker was placed here, and the sound, emitted sound is strike this paper here. And backside, so there is an electrode here, and but this part is moving. That's why this electrode is approaching and comes back cyclically. And between two electrodes here, so electricity is expected to flow. Sorry. This is also moving. So this is the LED. This is a real sound. Okay, so we observed that so large sound, when large sound is emitted, the brightness of the LED light was higher. Okay, and how much sound vibration was obtained? So we measured the situation and using 4 types of paper: and coated paper, matte coated paper, digit paper, and the thick paperboard. Okay, with different thickness, grammage, and the Young's modulus. Okay, so okay, I'll skip this one. And so to measure the vibration condition, so we put one sheet of paper here, and at under this table we put a loudspeaker, and the sound was emitted here. And on the back side and from the top, laser displacement meter was placed, and to keep monitor the distance from this point to the surface of paper. If this paper vibrates a lot, the displacement also changes a lot. Okay, and a different sound with different frequency was emitted from 40 hertz to 100 hertz. This is the maximum amplitude of the paper vibration measured by the laser displacement sensor. And usually, most papers show the higher maximum amplitude at the lower frequency, but only paper A, this shows the highest maximum amplitude at the at 100 hertz. So because sample A is a special callback, and it's coded paper, this is a very low grammage. So this paper is light, but high Young exposures, and so elastic. That's why this light and elastic paper gives the highest amplitude. So vibrated well at the highest frequency, like 100 hertz. Okay, and also we measure the 9 point. So the displacement sensor was only one. when we measure the displacement in the former experiment. But in this experiment, we set 9 laser displacement sensors. Okay, so yes, from the back side. So this is the a hole to monitor the vibration situation of the backside of this paper. So during emitting sound, we measure the displacement, okay, at the different 9 locations. And this is the result. And okay. And this is a low frequency vibration. So this is a 40 hertz. This is the lowest one in this experiment. The 40 hertz vibration, so 9 different locations, so the different mode of vibration. But at the higher frequencies, like this, higher frequencies, so 9 locations had the same pattern of vibration. That's why this means at higher frequencies, all the point of the paper is synchronizedly moving. Okay, this is the highest one. It's almost the same pattern was shown here at 9 locations of paper, from location 1 to location 9. Okay, this is, for example, this action was monitored using the image, like this. Okay. Okay, so thank you for your kind attention.
Thank you, Professor. Yep. Thank you, Professor Enamai, for that excellent presentation about how to utilize paper as biomass energy resource, and then about electricity generation or electricity harvesting from paper vibration by electrostatic induction. And then, ladies and gentlemen, I will remind you again that you have the opportunity to submit text question to our speakers by typing them into the chat box, and then you may send your question at any time during this presentation, but I will collect this and address them during the Q&A question. And then you are also welcome to ask question directly during the Q&A session by click raise hand button, and I will let you to deliver your question. And then, ladies and gentlemen, we are now moving on to the second speaker. Now, let's please welcome Associate Professor Muhammad Aziz. Professor Aziz, time is yours.
Okay, thank you very much, Bu Musharrafah. Assalamualaikum warahmatullahi wabarakatuh. Bismillahirrahmanirrahim. Okay, thanks to all of you, especially to my colleague also, Dr. Lucy, and also respected speakers, my sensei, and also my colleagues also, Dr. Hanif, and also my respected friends and also colleagues, Dr. Habib, and also Dr. Panji, actually. Okay, so today it is my pleasure and also my honor to give a talk to all of you. And in case that you have any suggestions, any comments to my talk for today, actually you can drop your question also in the chat box. Basically, I will talk quite in general case. So for any kind of special case, something like that, I think my colleagues, Dr. Habib and also Dr. Panji, they are very well knowing about the topics related to the energy. So you can also address the questions to both of them actually. So I just would like to share my screen first. Can you see my slide over there?
Yes, sir.
Is there no problems? Okay, thank you very much. Okay, for today, I just would like to talk quite general case, but I think it also covers several cases because in our laboratory in University of Tokyo, actually, we are also dealing with any kind of elemental technology development and also any kind of energy systems developments. And maybe in here also I will talk also correlated with the opportunities in terms that we would like to build any kind of new capital in Kalimantan also. And today's talk will be entitled to realization of zero carbons in future energy systems, quite general. Okay, as also professors, my professor mentions also that now we are all have two different paradigms, Industry 4.0 and also Society 4.0. Both of them are also basically brand. Industry 4.0 has been initiated by Germany, Society 5.0 by Japanese itself. Although Society 5.0 is more focusing on any kind of human civilization developments, on the other hand, Industry 4.0, they are more focusing on industrial developments. Actually, both of them are sharing similar values, similar ideas also. But I think the main focus also in the backgrounds over there are also quite different between Industry 4.0 and also 5.0. And because actually I'm also now living in Japan, although I'm in residence also, we are talking more focusing on the Society 4.0. So what is the big idea for the Society 4.0? Because I think it is also the big difference also when we are talking about the Industry 4.0. In Society 4.0, we are pursuing for is that we are utilizing several technologies, but actually this kind of technologies are not the main target itself. It is not the goals. This kind of technology, this kind of transformations that we would like to have, including any kind of digital transformations, any kind of maybe green transformations, GX, DX, or maybe any kind of corporate transformations, any kind of management transformations, or maybe etc. These kind of transformations are basically the tools itself. It's not the goals that we would like to achieve. The main idea for this one is that how far we can utilize all of the ideas and also creativity owned by the society, all of the stakeholders in the society to share, and also this kind of imaginations and also creativity can be utilized, can be facilitated together. So it means that all of the stakeholders, basically they have their own opportunity to take parts to the developments of the society itself. So the main idea is finally, we would like to also solve the problems as well as also create any kind of values in the society, especially the new values in the society. But as I mentioned previously, that any kind of transformations, digital, green, corporate managements, or etc., any kind of transformations are basically the tools. That they are not the goals that we would like to achieve for. What we would like to have is that I imagine that this is the tools that we would like to create. And the main idea is that how far we can also emphasize, we build our cultures, we build our values, we respect our values, we respect our history here. And finally, well, the main target is that how far we can enlarge, broaden, and also strengthen our capacity. So in case that all of the stakeholders in the community, they have great capacity, it means that these community also will be growing faster. And okay, this is the correlations or coherence between the SDGs and also with the Society 4.0/4.0. But for Indonesian case, I think we would like to emphasize, it's better to emphasize the 10 sectors in this issue, especially for the cities, energy, disaster, healthcare, agriculture, logistics, manufacturing, finance, public services, and finally also the tourism, because also Indonesia is also quite famous for the tourism itself. And we are talking about the energy. I think I have shared many times also related to this kind of triangles. When we are talking about the sustainability in the energy, minimally we will have these three pillars. We are talking about the energy security. But I just would like to underline the energy security not only deals with our capacity or our capability to supply the demand itself, what we need, but also how far we can have high quality of the energy. So we are not only talking about the kilowatt hours or any kind of megajoules that are demanded by the people, but also how we can provide this kind of energy in balanced manner, in responsive manners. So we are not only talking about the electricity in this case, although the electricity, yes, electricity needs very fast response, yes, actually, but it also valid for any other forms of the energy, including the heat, including the chemicals, including any others. So when we are talking about the energy security, we will talk about the quality, also about the quality. That's very important for all of us. And also the second pillar is correlated to the energy equity. This is also a very big issue when we are talking about the issue related to the renewable energy. What we are talking about the energy equity here is that it is also correlated how we can give to all of the community members to have any kind of opportunity, have equal opportunity to all of them to participate, not only to consume the energy, but also can sell or provide the energy itself. So in here, especially when we're talking about the renewable energy is quite really different with the fossils. Renewable energy, it means that it is widely distributed, it is thinly distributed. So it means that we cannot build any kind of large scale power generations and a kind of energy harvesting systems from renewable energy. It's very hard compared with the fossil fuels. Yes, for some fossil fuels, it is quite easy to build any kind of 1 gigawatt of power generators. Yes, that's quite possible. But for renewable energy, that's very challenging. So it means that when we are talking about the renewable energy share in the futures, it means that we cannot avoid any kind of participation or wide participation from all of the stakeholders. And finally, also we have also the environmental sustainability for years. In case that we have strong 3 pillars together and they are correlated, they are mutually correlated to each other. Actually, finally, also what we like to have is that we can have any strong energy resilience in our regions and our society. And we are talking also about the energy in society 5.0. What we are figuring out is that, okay, all the, I think that's the big task that in every era we are pursuing for is about the availability of renewable energy to all of the stakeholders. So it means that we are providing in both quantity and also the qualitative manners. And the second point is also related to the sustainable energy, clean and sustainable energy over years. So how far we can improve the share of the renewable energy here. So like Indonesians and also Japan, actually Indonesia has commitment to achieve zero carbon in 2060, Japan in 2050. These 3 decades or 4 decades in the futures are rarely very short time. So it means that we are being required to have any kind of clear roadmap to achieve this kind of zero carbons in next 4 decades or 3 decades further. And finally, also how far we can also improve any kind of decentralizations in not only in the energy systems, but also in building the city itself. So basically, we are not only focusing to develop one big city, especially for the capital one, but also we would like to also develop another cities which also need any kind of energy itself. And also I think the decentralizations of the energy, especially for power generation, for any energy harvestings, are really cannot be avoided, because when we are dealing with renewable energy, it means that it will be available across the country itself. And now currently, when we are targeting for achieving zero carbon 2060 and 2050, we are now in the transition period. So what we are having now actually decarbonization. Decarbonization can put in electrifications or non-electrification sector. Although yes, because the electricity is the most convenient energy form, secondary energy forms for us, it means that I think the biggest or the largest demand for the decarbonization will be in the electrification sector. So when we are talking about the decarbonization, it means not only limited to the renewable energy, it can also involve for the fossil fuels, but in terms that it can also avoid the CO2 generations. Yeah, CO2 is generated, but how far we can avoid any kind of emissions of the CO2 to our atmosphere. So that's also a big issue when we are dealing with any kind of carbon-based fuels in the futures. And also the third aspect is also related to energy productivity, or in other terms, also we can use the word of energy efficiency. And finally, also in case that we don't have another options, we cannot do any kind of decarbonizations, or maybe we don't have any technology for energy, a high energy efficiency, it means that we need to have any kind of scenario in which that scenario can produce the minimum CO2 emissions. I think this is also the CO2 emissions currently, but I think it's not really big deals now, because our energy consumption decreases, means that also the CO2 emissions in our atmosphere also decreases accordingly. And this is the indicators for low carbon growth in several areas, actually, globally accepted also. But I think all of you are also quite well known about this one. Also, this is minimum of greenhouse gases. Also, I think it's quite familiar also. What I would like to talk about is related to the how far in the futures we can move to any kind of more integrated energy system in the futures. We are quite familiar with the word of IoT, Internet of Things. But also in the energy sector, also we are also dealing with any kind of IoE, Internet of Energy. How far we can connect all of the stakeholders, including the big power generators of the years, and also with the consumptions. And also, we are also playing together with the big data. All of these players, all of the stakeholders, especially renewable energy and also the consumption side, they are sharing the big data correlated with some consumptions, also correlated with any kind of power generations, or any kind of maybe atmospheric conditions. In here, it means like weather conditions, temperatures, wind, etc. So it means that we can use any kind of data processing technology, including artificial intelligence, including digital twin technology, to correlate this, to predict and also to forecast the energy generations and also the energy consumption in simultaneous manner. So this is also related to big data, I think, but I think all of you also quite familiar also with this one. But I think the big important thing when they are dealing with the big data also, it is correlated not only with the volumes, velocity, and also variety, but also with the veracity. Veracity, it means that we need any kind of very trusted data, and how far we can avoid any kind of fake data, any kind of untrusted data over years. So I think that also we need any kind of technology to avoid this one, to avoid this kind of fake and also untrusted data. And when we are dealing with any kind of community energy management, I think, yeah, it is the concepts in Japan actually, but not all the words adopted this kind of technology, this kind of concept actually. In several areas, they are adopting any kind of smart city concepts. So more distributed, not only related to any kind of SAMs or community energy management systems over here. So in the futures, actually, we will have any kind of decentralized energy systems over years. We will have any different microgrids here, and also any kind of power generations, and there will be any kind of distribution system, transmission systems, and finally also we can have any kind of the wholesale energy market that can be shared, can be accessed by all of the stakeholders, including also with currently using currently consuming customer. So customer basically not only consumes the energy, but also in the futures in the same manner, in this similar time, actually in the same time, they can also behave as the energy producers. So we are quite familiar also with the word of prosumers, producers and also consumers. So it is the big idea also correlated when how we can move the trends in the futures. I think this is the current conditions that we are living now, our conditions currently. We have the baseload generators. Basically, it comes from coal, it comes also from geothermal, it comes maybe like Japan, we have also a nuclear power or etc. And usually the price of the electricity is the lowest. Okay, like the coal and also for nuclears, maybe the price will be about 8 cents, 10 cents per kilowatt hour, something like that. And also we have also very fluctuating, or maybe in here also any kind of middle load generators over years, including any kind of gas turbine and also any others. Okay, and finally also we have demand like this. Currently, actually, the problem is that we are now trying to adopt to increase the share of renewable energy. But as we know that renewable energy, the characteristic of the renewable energy, like the solar, like the winds, or maybe any others, also they are fluctuating. Yeah, hydropower is also fluctuating, but it is seasonal fluctuations. Seasonal fluctuations. The time frame is quite little different. But for the solar, it can fluctuate in relatively in seconds frames. So in here, how far? And currently, actually, what this problem is that this kind of increasing, fluctuating renewable energy should be covered with any other middle load generators, yeah, including the gas or any others. And finally, the CO2 emissions is not decreased significantly in total. In the case also similar with the Germany. Germany actually they have big commitment currently to phase out or to reduce the consumption of renewable or fossil fuels. They would like to increase the share of the renewable energy, okay, like the solar and also wind in the northern part of Germany. But the problem is that what they are facing now currently actually because of this kind of fluctuations, and also there's also limitations to deliver or to transmit the electricity generated at the northern part of Germany to the southern part of Germany. Finally, the case of the curtailments. The wind turbines in the northern part of Germany is curtailed. Yeah, some of them are curtailed. It is also similar also with the Kyushu area also in Japan actually. And the problem is that because finally this kind of fluctuations is covered by gas-based power generators. And finally, what is the result is that we cannot achieve any kind of significant CO2 emissions in total. And what we would like to have in the futures, okay? I think because the consumptions of the coal itself is decreasing. Finally, also I think the baseload generator also will decrease, and we need also to because we would like to increase the renewable energy share in the total. So it means that we would like to avoid any kind of curtailments from renewables. Okay, so finally we need any kind of adjusting generators. How far we can play or utilize this kind of adjusting generators. Adjusting generators here, I think is quite different with these middle load generators. Why I use the word of the adjusting generator? Because we need any kind of responsive power generators to cover the fluctuations. So we can have any kind of like battery, like hydropowers. Yeah, hydropower has been adopted by several countries actually. But in the futures, we need several technologies to responsibly respond to any kind of fluctuation in the grid itself. So finally, we can avoid any kind of curtailment from the renewable energy sources. So in here, we can focus on how far we can use any kind of several technologies, including vehicle to grid. So how far we can utilize the electric vehicles distributed across the country to support that, to support the fluctuation, to support the grid, and also how far also we can use the hydrogen also for adjusting generators. So the big idea for hydrogen is not for the baseload generator over years because the price will be really low over years, but I think we will be focused on the adjusting generator. So we can have premium price of the electricity or services over there. So this is also a big idea for the Young Capital Plan. It's in Indonesia, but the problem is that because we could see over years, the grid are not well connected between the western, also the eastern part of the Kalimantan itself. So how far, in case that we would like to increase the sustainability in terms of the energy in Kalimantan Islands, the big issue also correlated how far we can connect these two great transmission systems from the between the east and also the west part of the Kalimantan also. And also another part, and the problem is that because Kalimantan also is tropical, so it means that the characteristic of the tropical area over here is that high temperatures, high humidity, right, and also high rainfall. The problem is also low wind speed. So it is quite difficult for us to adopt any kind of solar or wind-based power generators over years. So another scenario for maximizing the renewable energy, the resources owned by this island, I think also need further attention for all of us. Actually, I think we have big hydropower also in the eastern part of the western part of the Kalimantan over years, but the problem is that correlated with the grid itself. And also, actually, we have also several resources for the biomass also, and also the huge part of the energy supply also by coal and also the gas, oil also actually. But how far we can move for the decarbonization technology for the coal itself? I think that's a really big deal for all of us. Yeah, I think this is dealing with any kind of development of smart city, but I just would like to avoid to discuss this once. I think it's because of limited time also for today. What I would like to talk today that also correlated with how far we can have any kind of smart energy systems in our energy systems for the futures. It is correlated also with the smart electricity grid, and also as I mentioned previously, it is correlated with the decentralized energy systems for all of us. And also when we are talking about the distributed or decentralized energy systems, how far we can facilitate all of the resources available. I think each area they have their own characteristics. Okay, so we cannot just copy that scenario from other countries or from other area to our own area. It is really, really difficult. It is maybe the feasibility will be quite low. So it means that over years, how far we can have any kind of capacity or capability to develop the characteristics on by our own regions. And as I mentioned previously, also when we are dealing with any kind of decarbonizations, what kind of carbon-free secondary resources that we can have in the futures? Okay, electricity. Yes, electricity is very, very convenient for all of us. It can be converted completely to the heat or any other forms of energy. But unfortunately, in terms of energy security, we cannot lay on or depend on one forms of the energy itself. We need any other forms of the energy, especially for the chemical energy, because the density and also the convenience to be transported or stored. So we can have, and for the chemical energy, I think when we are dealing with carbon-free, so we are avoiding any kind of carbon-based fuels over years, we can have hydrogen-based fuels, including hydrogen, ammonia, or etc. And also, metal fuels are also quite promising, but unfortunately, these kind of metal fuels still need further developments. Some researchers in Netherlands and also in Canada, they are focusing for developing metal fuels for the energy sectors. Also, we can have a heat over years. Yeah, this is very, very conventional energy forms in our life, actually. So we were actually, this is the big scenario for our laboratory in Tokyo now currently. When we are dealing with any kind of electricity and also chemical energy, carbon-free and chemical energy over years, that how far we can communicate both of them, how far we can have any kind of mutual conversions or utilizations together between the electricity and also the chemical energy, or in this case, especially we are focusing on the hydrogen-based chemical energy. Both of them can be stored, okay? Yeah, although for the electricity, it can be stored, especially in the chemical energy, especially for the battery. And also both of them can be generated, can be produced by from any kind of primary energy resources, including fossils, including renewables, nuclears, or etc. And especially for the hydrogen, also is the materials. So in here, when we are dealing with the hydrogen and also ammonia, hydrogen and ammonia are materials. And also the second thing is that both of them also can be fuels. So how we can communicate how we can utilize them together in the futures, that also will be a big challenge for all of us. This is the utilizations feasibility for the hydrogen ammonia things. But in here, actually, although there are some technologies for the passenger cars, but unfortunately, I don't show any passenger cars over here. Because what? Because I believe that for the passenger cars, small scale vehicles, I believe that electric vehicles will be the winner compared with the hydrogen itself. Hydrogen, what is the big focus of the hydrogen, as I mentioned previously, also that it will play on the adjusting generator for power generation itself, and also any kind of mobility, transportation sector, especially for transportation sector, which demands any kind of high gravimetric density of the fuels, especially for the aviations, maritimes, and also any kind of train or etc. And this is also the big scenario, how far we can have any kind of repositioning of the hydrogens and also ammonia. As I mentioned previously, that in case that we just use hydrogen ammonia as the base load, it means that the price of the electricity or the profit that we can have is very, very low. So it is relatively not competitive. So how far we can adopt, especially in the initial period maybe can valid for about 2 decades, 3 decades, or etc., especially before the hydrogen economy itself, we can utilize this kind of hydrogen, also ammonia, for any kind of ancillary services, for any kind of adjusting power generations. So in here, we can compete, we can utilize hydrogen actually for, or I think will be this kind of gas turbine, internal combustion engine, also for fuel cells. It will be very competitive with the battery itself, especially for the fuel cell. And as I write also over here is that from the left to right side, it means that it has higher ramping rate. So it means that it can responsibly, it has quite high responsiveness, okay? And also the problem also that it has higher active powers. I don't know whether you are quite familiar with any kind of active or reactive powers or here, but actually the active power usually currently in our market today, the electricity is basically measured for the active powers, although we need also the reactive power. Reactive power usually utilized for motors or etc. And also this is the integrations, but I think not all of you quite familiar because it's quite technical. So I just would like to move on. This is when we are talking about the realizations of zero carbon in 2060, especially for the Indonesian case. And we are dealing with the hydrogen itself, how far we can have any kind of quite achievable, measurable, and also achievable hydrogen's roadmap for the futures. And in here, I divided to 3 different stages. The first stage, I think, is about 15 years, 1 decade and about 1 decade and 5 years, something like that. I think until 2035, we can start from the pilot and also export orientations. So basically, it is quite different with the Japan case. Japan, okay, in Japan we have technology and also we have investment, but in the Indonesian case, it is really different. We have quite low technology mastery and also any kind of investment also. So I think, but on the other hand, actually we have resources. So it means that I think export oriented will be the first priority for all of us, as well as increasing any kind of social acceptance and also creating any kind of markets, both globally and also domestically. And in the second stage, until 2050, something like that, I think we need to build, initially build any kind of infrastructures. And this is, until this one, I think until this 2050, it is very hard to get any kind of hydrogen economy. In here, we just spend the money, we just spend the investment. And after that, hopefully, after the increase of the social acceptance in the community and also the infrastructures, some part of some area or maybe some part of the area has been devised by hydrogen infrastructures. So basically, we would like to achieve any kind of hydrogen economy, although it is very, very challenging. But actually, because we have different resources, especially for the coals, low-rank coals and also industrial waste or etc. I think these kind of resources also potential to be converted to hydrogens. And this is the scenarios I think is quite feasible for in recent case. As I mentioned previously that we have different resources, especially for not effectively utilize low-rank coal for years, and also for the any kind of industrial and also agricultural waste. As Professor Enomai also mentioned previously, including the black liquor, including the palm waste or etc. Actually, we are also quite rich of that actually. So it means that when we can utilize this kind of resources, coals and low-rank coals and also industrial and agricultural waste, I think that also will be quite promising to be converted to hydrogen. And hydrogen can be maybe first initially can be exported, or it can be combusted together in the existing coal power plant. Or otherwise, in case that we have any kind of hydropower generation, but it is located in very, very remote area, and there's no grid connecting to this area, we can convert also this kind of power generated from hydropower to hydrogens, and then hydrogen maybe can be converted to ammonia and can be brought by any kind of trailer. I don't put double circle for the natural gas because what? Because I believe that natural gas will be the main player during the energy transitions. Because what? Compared with the coals, it is quite convenient. Yeah, it is quite convenient, and also it has lower CO2 emissions compared with the low-rank coal. So I just put triangle, although it can be converted easily to hydrogens, but I think I believe that this kind of natural gas or methane itself will be have main role during the energy transitions itself. Also for the storage and transportation for the hydrogens, actually, I put triangle for the methanol because what? In methanol, as we could see over here, that there is still carbon over here. So it means that in the utilization sector, in case that we adopt methanol, it means that we still release the CO2. And also for the utilization side, I think the big ideas is that how far we can start from any kind of infrastructures we have today, including the existing coal power plants and also diesel systems. So because hydrogen actually can be blended, can be mixed together, can be combusted together with the coals, with the biomass actually. So it means that in case that we can adopt for the combustions and also for mixings for the diesel, I think that's will be quite a good move for in a recent case. And further, also in case that we have quite for maybe for adjusting generators, in case that we have quite open market in the futures, maybe we can adopt any kind of fuel cells to provide any kind of adjusting generators. So also this is another technology that we have also demonstrated in Denmark actually, because what in Denmark is a really flat country. It has no mountains areas, so it means that they are they have difficulty to build any kind of hydropower for energy storage. So that's the idea, is that they encourage the citizens to purchase the electric vehicles, and finally we adopt any kind of what we call as the vehicle grid integration technology to utilize the distributed electric vehicles, whether these kind of electric vehicles are parked in our homes or maybe in offices or shopping malls or etc. As long as they have connections with the grid, or it is connected to the charger, and also it has contract with any kind of aggregators or operator of operators. So it means that all of these electric vehicles, basically they can have any kind of ancillary service to the grid. So it means that they can deliver the electricity, or in case that there is any kind of surplus of electricity in the grid, they can absorb the electricity. In our case in Denmark, we have project 3 years there. Actually, the benefits is quite big. We can have any kind of passive income from the user. The users can enjoy passive income by joining this kind of systems. But I don't remember well in euro. In 1 year, actually in euro, it is about 20,000 euro of profit. So it means, I think in case that I calculate for rupiah, I think per month it will be about 1.5 million or 2 million rupiah per month for the passive income by joining this kind of services. Okay, and this is also the projects that are distributed in around the world actually. And I think because I'm running out of time, I think today, and also it is, I think the last talk that I would like to deliver today, biomass. Yes, biomass basically is very old. The history of biomass is very old. It's very conventional. But unfortunately, until now, when we are talking about the biomass, we are still facing about the problems of the economy. Biomass is still quite costly, or etc. However, in the futures, we can utilize this kind of characteristics, yeah, including like storability, flexibility, or etc. So it means that we can reposition, we can redefine the price of the biomass, not only as the power generator, especially for the base load, but how far we can reposition the biomass itself for the adjusting generator. So it means that when we level up the biomass for the adjusting generators, so it means that we can have more premium price or higher price compared with the base load itself. So I think this is also another idea of the technology that's also correlated in our laboratory now currently. But in case that you have interest, maybe you can access to our lab website, and you can have further detailed information related to what we are doing now currently. So we are doing currently now with this kind of technology, what we call the chemical looping technology. This kind of chemical looping technology is not only limited for the fossil, but also for the any kind of renewable energy, including the biomass or etc., any kind of waste, etc. We have 3 different reactors which are correlated. They are looped together over years. We have fuel reactor or reducers. We have also steam reactors. It is usually also called as the oxidizers, and also the air reactors or combustor itself. So it means that in the fuel reactors, the fuel, which can be any kind of solid, liquid, and also gas, is converted to CO2. You can see over years that it is converted to CO2. And finally, the reduced oxygen carriers is going into the steam reactors or oxidizers, and we react with the steam over years, and we can produce high purity hydrogen itself. And finally, because we need to return back the oxygen carriers to the initial state, we have air reactors over years, and we react with the oxygen from the air, and finally we release nitrogens. So by these one modules, actually what we are targeting for is that we can separate CO2 as well as produce the hydrogens. So as the basic concept of our laboratory is that we are dealing with any kind of carbon-free fuels over years. It means that we are, in case that we are dealing with any kind of carbon-based fuels, we would like to avoid any kind of CO2 emissions. So we separate CO2, and finally maybe we can utilize or maybe sequester CO2. And I think that's all the things that I just would like to talk today. There we have any different challenges, different homeworks for our country actually, especially for the decarbonizations, improving the energy efficiency, how we can also increase the renewable energy share in our energy systems, and also related to the security. Security, as mentioned previously, not only dealing with the quantity, but also in qualitative manner. And also how far we can have any kind of smart systems. We need to build any kind of big data systems, historical data, blah, blah, something like that needs to be built. And so it means that we can connect all of the data, and we can predict, and we can have any kind of appropriate decisions, appropriate for forecast, accurate forecast for us in our energy systems. And also the important thing is that we need to reform the market. With the current market, it's really impossible. Okay, we need to have any kind of open market which can facilitate the participations from all of the stakeholders, and also resilience, social, and also general balances. Thank you very much for all of your attentions today. And so in case that you have points to be discussed further, or suggestions or comments, etc., it is my honor to welcome all of you. Thank you very much, Musharrafah. Sorry if I make several mistakes. Thank you very much. Wassalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. Thank you very much, Professor Aziz. Thank you for that amazing presentation about toward realization of zero carbon in future energy system in era of society 5.0, and of course about several transition strategies need to be pursued as well. And ladies and gentlemen, I remind you again, if you have any question for Professor Aziz, you can type them into the chat box, and you may send your question directly in the Q&A session. And then now we are moving on to the third speaker. Now let's please welcome Dr. Abdul Hanif Mahadi. Time is yours.
All right, thank you very much. First of all, I would like to thank you, the committee, for inviting me to present this keynote speaker. And also, I'd like to thank you, all the presenters and keynote speakers and my colleagues, and also all the participants for joining this event today. So just to introduce, my name is Dr. Abdul Hanif Mahadi. Greetings from Brunei Darussalam. I'm from Center for Advanced Material and Energy Sciences in University Brunei Darussalam. I'm currently the Deputy Director of the Center, and also I'm the research lead for the Catalysis Research Group at the university. So let me just share my PowerPoint. Okay. So today I will be talking about catalyzing sustainable hydrogen energy production and storage. So it's sort of that continuation from what Professor Aziz has presented as well, regarding how hydrogen energy will be quite important, especially moving towards the carbon-free energy climate, for example. So in this case, I'm talking more in terms of the technology involved, and also our current research that is happening in CAMES, or the Center for Advanced Material Energy Sciences, with regards to hydrogen energy. So we are dealing with the production and the storage and the technology, or the research and development involved within this hydrogen energy production and storage. So let me see if I can pointer. Yeah. So the title is a play word of catalyzing sustainable hydrogen energy. So it's first of all catalyzing in terms of how can we make hydrogen energy becoming more prominent, or develop the technology to get the hydrogen energy. As what Professor Aziz mentioned, it will take at least 10 or 20 years for hydrogen energy to become more economical or more sustainable for industry, for mass industry usage. So we are using, so some technologies can be developed to catalyze this hydrogen energy development. And one of them is the use of catalysis, and meaning that catalyst materials. So because once we noticed that hydrogen energy mainly involves a lot of catalyst materials, and part of the CAMES main research focus is to develop these catalyst materials, or develop novel materials for the use of hydrogen energy production and storage. So just some chemistry or some characteristic of hydrogen. First of all, it is the first element. Has a molecular weight of 2, so it is quite a light atom, or quite light element. Mainly it is a gas at room temperature, so it makes it quite hard for logistical reasons or transportation and some, but the reason why we are looking into its hydrogen energy currently is because of these advantages where what is considered as a renewable energy, depending on the sources. So again, depending on the sources, it can be renewable or non-renewable, but it can be one of the clean energy source, because once you burn hydrogen, it only produces water, so it doesn't have any carbon dioxide output, or it doesn't produce any carbon dioxide. And also it is non-toxic, and also is highly efficient because it can bring quite a high energy density if you design correctly. But some of the disadvantages, currently it's expensive, is because the technology is not mature yet. So the current technologies that we have are not commercially viable. This is due to because of storage complications, for example, because it existed as a gas state. So it's either we need to cool it down or pressurize it, which we'll discuss later. And also because it is currently not the safest, which is similar to other source of energy as well. But for example, like nuclear or even oil and gas, they are considered unsafe in terms of flammability. But again, as technology improves, then we can improve on the safety and also the logistics or the storage complications. And some disadvantages as well, it can be dependent on fossil fuel, which we'll discuss later. So currently, hydrogen, us in Borneo, we have quite some advantage of hydrogen, meaning that currently, mainly hydrogen is produced from natural gas, which is CH4 or methane. So for industrial reasons, it is still the most economical way to produce hydrogen is still through natural gas. But it has a disadvantage, meaning that because it produces carbon dioxide or carbon monoxide, so that makes it, they call it a gray hydrogen. So currently people have been coloring hydrogen, although we all know that hydrogen is colorless and we can't even see them. So they just color it as because of technicality. So meaning that blue hydrogen is something, the hydrogen derived from natural gas or the gray hydrogen we call it. But it has some sort of carbon capture installed with it. So that means then you will offset, or even you will offset the carbon dioxide production out of it. And secondly, the green hydrogen, this is sort of like the holy grail, or what we are trying to aim into when we talk about hydrogen, is when the production of hydrogen from renewable energy with zero carbon footprint. And this is mainly through water splitting. So it can go from electrolysis, photocatalysis, or our theme for today is biomass derived, which we will discuss later on. So mainly electrolysis and photocatalysis, again, they use all this biomass electrolysis and photocatalysis, which mainly take use of some novel catalyst as well. And even for blue hydrogen, when we derive natural gas, or produce natural gas, when we produce hydrogen from natural gas, from steam reforming and water gas shift reactions, although the technology has been around for almost 100 years, but we all know that it's been using some catalysis technology as well. So just as introduction, what is a catalyst? So a catalyst, the technical definition is something, a material or the substance that speeds up a reaction. So if you look at the reaction profile diagram, usually a typical non-catalyzed reaction goes through this profile, where you can see that from the reactant energy to the top, they call it the transition or intermediate state, and this is the delta E in a way that, or the activation energy. So any reaction without a catalyst will need to go over this barrier first, no matter where the energy of the product is. But with a catalyst, mainly it will provide alternative routes, for example, and that will, in turn, if you look at the reaction diagram, will lower the activation energy. So that means, in terms of real life, then the reaction can go to from either lower temperature or even lower pressure, which means more energy is saved. So the blue hydrogen, like I said, it's hydrogen derived from natural gas through the process of steam reforming. So mainly, but this is, if it's just steam reforming as how it is done now, it is still considered a gray hydrogen, but anything that produce carbon dioxide, if we employ some carbon capture, utilization, and storage technology, then it will just leave purely hydrogen. So currently, there's a lot of research involved in the CCUS, whether it is the capture or even utilization, and also even the storage. So typically, in natural gas, how it's formed, it's using these two reactions. Firstly, in a steam reforming reaction, where you start off with the gas, the natural gas CH4, and then you react it with steam, and then you produce this thing called syngas. And this again uses a nickel-based catalyst, but even with the catalyst, it needs up to around 1000 degrees Celsius and up to 25 bars. And then after that, with the syngas, you react it again with water to produce CO2 and hydrogen. This is just to increase more hydrogen of the mixture. Again, it's using some iron-based catalyst, and it has some sort of two ways, which is a high temperature shift or low temperature shift, depending on your reactor as well. But the overall reaction, if you see here, if you put these two together, you're basically reacting methane with water, but it produces CO2 here. So if you just, this is currently what is happening in basically gas downstream processes where they produce CO and H2 syngas first. And for example, like production of ammonia or methanol will have to go through this process. But the key here is anything, even the blue hydrogen will need some sort of catalyst technologies to make these reactions happen. So even how to get rid of the CO2 again is using some catalyst things. So this is just example of some picture of what in the industrially how the steam reformer and the water gas shift reaction takes place in the gas downstream industry, for example. So what do we do with the CO2? So what first thing is either we capture it and then we concentrate it and then we store it, so put it underground or something. And then what we do in CAMS is we tend to concentrate on the utilization part, which means transforming CO2 into fuels, for example. For example, so you can react it with hydrogen again to make CH4, and also, or even to make methanol, for example. So you can have CO2 and then transform into carbon product, which can be used again as fuel. And this there exists to be some carbon capture or carbon dioxide cycle with all these technologies that enables to basically use carbon dioxide in a more economical or even more greener way. So moving on to the green hydrogen. So again, green hydrogen is mainly production of hydrogen from electrolysis. So it uses this process called water splitting. So it splits water into hydrogen and oxygen. So mainly, and using electric current because it's electrocatalysis. So currently it's still the most expensive method. And the game here is whoever can make the cheapest renewable energy is the winner in this game, basically. So, and this electrolysis, if it's done by, for example, gas turbine, then it defeats the purpose where you still have carbon emissions. So for green hydrogen, the electrolysis has to be powered by renewable energy, for example, wind, hydrogen, solar, or nuclear, and it makes use of the electrolyzer. So in here again, there involves a lot of catalysts where these anodes and the cathodes are mainly catalyst materials. So it makes use of these things called electrolyzers. So currently, the challenge is why it's still quite expensive is because it has a high kinetic barrier. So kinetic barrier, if you still remember from the previous reaction profile diagram, hydrogen splitting has a quite high activation energy. So in terms of electrolysis, they call it high overpotential. meaning potential of over 1.25 volts. So you have to put in this amount of energy just for the reaction to start. Secondly, currently with the materials that can do this is the cathode, or we call it for the HER hydrogen evolution reaction, where the hydrogen is produced, is still quite expensive, and even the anode material where the oxygen evolution reaction to produce the oxygen are still quite expensive. For example, they use platinum catalyst as an electrode. So again, with this development, the research is mainly firstly to bring down the kinetic barrier. So we need to use some sort of a novel catalyst or new catalyst, new materials to bring down that is very reactive to bring down the kinetic barrier. And but secondly, it needs to be economical as well. So it can't be using like gold or platinum or palladium, which can be expensive. So in the materials research, people are researching and developing new materials just to bring down, to take down these challenges in electrolysis. So mainly people have developed, or researchers have developed different types of electrolysis, mainly PEM, proton exchange membrane catalysis. This still makes use of this platinum materials. So this is still the most effective, but also the most expensive. So to bring it down, and it has to be in acidic environment. So that means the materials will need to stand in highly acidic conditions. So to bring down this cost, people start to use alkaline electrolysis. So of course, the cost is lower, but it suffers from lower activity, for example. And to do that, so to play around with this, people even use high temperature solid oxide water electrolysis, where they put in temperature. So use solid oxide, but they have to have a temperature input as well. So each of them have their own advantages and disadvantages. So in CAMES as well, and also in the research world, so we are trying to see, again, like I said, the game is to bring down the over potential, and also the economic, to make new materials to make this electrolysis economical. So typically, the fundamental research will involve using a lot of Tafel plot, where they use the I versus E graphs, and they will see they can calculate like how the over potential and the current density. Then they will see this Tafel slot B and then A to compare how good the catalyst is. So the ideal catalyst is where you have very low electron transfer kinetics and high exchange current density. So it'll make this sort of like Tafel plot where it doesn't tail off, it doesn't tail far off. So this is just summary of some of the HER electrocatalysts. So for example, like I said, if you use a platinum base, you can still have quite a high activity, for example, whereas when you go towards non-metal based, then you have quite lower performance. Secondly is to use photocatalysis. So that means instead of using electricity as an energy input, you use the energy from the sun as an energy input, in a way, photocatalysis. So energy from the sun, it can be in terms of UV or even in terms of visible light. So this makes use of semiconductors, for example, TiO2, perovskites, cadmium sulfide, or quantum dots. But it has some sort of requirements. First of all, you need to have semiconductors will have these band gaps, and this band gap will need to have more than 1.23 so that it exceeds the band gap of hydrogen water splitting as well. And again, the band gap preferably needs to be in a visible light region, because from our sun, the mostly is dominated by visible light region. And of course, the game here again is to have minimum exciton recombination. So basically, how photocatalysis work is you have this electron and holes, and this electron can be used, and this holes can be used to react with hydrogen to make radicals and to split the hydrogen. So basically, the main problem of photocatalysis again is the band gap either be too high or too low, because if it's too high, then it's very hard to excite it. And also the electron, they call it a positron recombination, this electron or the hole, the exciton recombination. So meaning that once you produce this electron or the holes, then it can recombine it with something else. If you have some charged species here, then that makes your reaction less likely or even less effective. So in photocatalysis, the performance is measured by quantum efficiency. So this is just some of the notable work done in Tokyo University as well by Kanazari Dolman, where they have made a large-scale solar hydrogen solar panels. So instead of solar panels, so it looks something like a solar panels, but the panels are sprayed with this photocatalytic materials, and then it produces hydrogen, and they come up with some system to extract this hydrogen. So another method is using this PEC or photoelectrochemical method. So this makes use of both photocatalysis and electrocatalysis, where you use this electrocatalysis and so where this electrode materials are both active in electrocatalysis and also photocatalysis. So mainly people use, in the research, you use OER as a photoactive materials. And also this helps to bring down the voltage or the overall potential. So this makes use of some type 2 heterojunctions or PN junctions. And also we try to make use of electrode that is photocatalysis that is in visible light region. So speaking of our today's theme, how does biomass come into the picture? So another green production is to produce hydrogen using biomass. So we have published a paper just recently as well, where we use photocatalysis to produce biohydrogen from cellulose biomass waste. But again, this is using some sort of metal catalyst. So in this way, there are a few ways to do it, either using photocatalysis or thermal catalysis. But in this case, we use a photocatalysis that where we play around with different metal with TiO2. So for example, we have palladium metal and copper and cerium and nickel metal. And of course, the best one we get is from palladium TiO2 photocatalysis. And we achieve the best hydrogen production from holocellulose instead of cellulose. So, and we use some sort of cotton linter cellulose. So you can read more about it in this biomass conversion and biorefinery paper. So we will have this sort of, so the idea is we will have this sort of cycle where the hydrogen cycle or the hydrogen economy will just depend on blue hydrogen and green hydrogen in terms of production. And then when we have storage as well, and it can be used for either transportation or energy for a chemical industry or even power generation. So next up, so we've done with green hydrogen or blue hydrogen production. Now we have produced the hydrogen. What do we do with it? Mainly to store or to, the other challenge is to store or even to transport it. As you know that gas, hydrogen exists in gas. So what do we do with it? So there are mainly two main areas on hydrogen storage, mainly with physical base and chemical base. So in CAMES, and what we do, we mostly concentrate on the chemical base of hydrogen storage. But whereas just to complete, I will show you some examples of physical base hydrogen storage as well. So mainly just to go quickly, when we look at a critical point, we need to go down to minus 200, below 250 degrees Celsius to make it compressible liquid as well. And so you have to play around with a high pressure and lower temperature to make it into a liquid phase, for example. So the first thing is to compress it. This is still in gas phase, but you have more concentration of hydrogen. This is pretty much used in NASA, for example. So next one is to also cool it and also compress it. Then you can get more hydrogen per volume as well. And also either you can liquefy hydrogen at below minus 253 degrees Celsius. And this is pretty much used in launches for the rockets to go to outer space, for example. But just to concentrate, we are mainly working on chemical base in CAME. So again, there are few, they call it hydrogen storage materials or carriers. Some of them are metal hydrides. These are mainly the concern in this hydrogen storage, mainly in LOHC or organic hydrogen carriers, or ammonia as a carrier, and also adsorbent. But these are some specific requirements if you want this material or chemical to be hydrogen storage or hydrogen transporter. First thing, it has to be liquid at room temperature and pressure, and also it needs to have high hydrogen density, and also it can hold the hydrogen without minimal loss of hydrogen. So it has to be sort of stable and unreactive. But also, as for logistics purposes, it needs to be non-corrosive as well, because otherwise you need to come up new materials or new metals to hold these chemicals. So we'll go through it one by one. So firstly, metal hydrides. So this is something that has, for example, metal magnesium hydride or lithium aluminum hydride or sodium borohydride, which is these are sort of like organometallics or sort of semi-organic materials, but it suffers low hydrogen percentage weight and it suffers low reversibility as well. So, but just for example, you have this phosphanable ring, where you can fix hydrogen into the phosphine group and the borane group as well here. But as you can see, of all this big structure or chemical here, you can only fit one atom or two atoms of hydrogen here, which makes the suffer low hydrogen percentage. So we move into organic hydrogen carriers instead, or what people in the industry call it LOHC, liquid organic hydrogen carriers. So currently, these are the LOHC that's been identified as a promising material or substance to carry hydrogen, mainly formic acid or methanol, toluene, and this nitrogen heterocycles. So mainly it's because it has high gravimetric storage density. But again, to store and also first thing you have to store the hydrogen and release the hydrogen again. So they make use of catalysts as well. So one example, formic acid. So formic acid has this structure where it's C double bond OH. So it is something like your vinegar, ethanoic acid, but with one carbon less. Some disadvantage is it produces CO2, but the CO2 again, if you make it into a cycle, you can recycle it back to formic acid, for example. But it is quite clean. It can produce hydrogen. But the problem for this is, first you have, when you dehydrogenate, you produce hydrogen and CO2, which is quite good. But also it can have a side reaction where it goes, dehydration reaction, where it produces H2O and CO. So the problem with this is, even though you have very small dehydration percentage, this side reaction produces CO, which can sort of poison the catalyst that's being used for dehydrogenation reaction. So first you have to come up with catalyst materials that mainly produce dehydrogenation reaction. And also you have to have catalyst materials that can stand carbon monoxide poisoning. So we have some paper in ACS catalysis as well, where we use formic acid, when we study the formic acid, carbon monoxide, when we use formic acid electrocatalytic oxidation to produce hydrogen, when we use palladium catalyst, and we use some palladium with cerium oxide to make it more susceptible to carbon monoxide poisoning. So if you want to read more about it, please feel free to read the ACS catalysis in this paper here. Just to share as well, currently we have, which is it? Oh, I will answer it later. So currently we also have this pilot project, they call it AHEAD project, where they use toluene to store hydrogen. So they call it the spiral hydrogen. This is in collaboration with the big Japanese chemical industries, for example, Chiyoda and Mitsubishi Chemicals as well. So in Brunei, they produce the hydrogen using natural gas, which is still hydrogen storage. But this pilot study is more towards how to see the efficiency in transporting hydrogen using this MCH or methyl cyclohexane. So for example, so they use the toluene, and then once you react it with 3 hydrogen molecules, you hydrogenate it into methyl cyclohexane, and then you bring it into the ship, and then transport it to Japan. And in Japan, where they dehydrogenate it and recycle back the toluene, and then this comes into a cycle. So far it's been ongoing for about a year or almost 2 years, and they've been getting good results with this technology. Also, this has been mentioned in Professor Aziz's lecture as well about ammonia. So ammonia again is very is one of those highlighted or even promising material or substance to for hydrogen storage or hydrogen energy, mainly because ammonia currently is being used to produce urea, but now you have to sort of repurpose it to produce hydrogen, and it has quite a good hydrogen density in terms of and ammonia, and also it is quite clean, where you only produce nitrogen and hydrogen. So it is liquid at room temperature and pressure, and only produces hydrogen and not nitrogen. But the problem with ammonia as a hydrogen storage or hydrogen carrier, to produce ammonia itself is produced by this process called Haber-Bosch process. But the problem is ammonia using this Haber-Bosch process is still quite inefficient, where they use very high temperature and high pressure. But currently, using better catalysts as well, researchers can lower down the pressure and also the temperature to produce this ammonia production. So the current game is here, if you can produce ammonia at a very more efficiently, meaning using renewable energy, for example, just using solar or wind, then ammonia will be more promising, or even can be used for more economically viable, or even energy viable for mass usage. There's also some sort of ammonia related products, for example, hydrazine and amine borane, which can be used for hydrogen carriers as well. So for example, so that's one side of the story. The other side is, how do you release back this ammonia back and get the hydrogen back? So you need some sort of good catalyst as well that can reform or do an ammonia reforming reaction. So we have done some, again, we use some photocatalysis using like palladium or copper, where again, palladium is quite good at reforming this ammonia using photocatalysis process. So the next one is devising some material or high surface area materials to absorb this ammonia. Again, this is less likely to be made into the economical, into industrial use, mainly because it is the hydrogen is it has weaker hydrogen retention. So mainly it just uses this high surface area materials or porous materials, for example, metal organic frameworks or zeolites, for example, which have pores to store hydrogen in there. So it is just using adsorption. The chemistry is just, there's no actual chemistry, actual chemical reaction. So they just use hydrogen as an absorbent. So that's why they need to use very porous and very high surface area materials. But the drawback with this is it has a weaker hydrogen retention. So that means if you transport it for a long time, then the hydrogen can just get dissolved over time as well. So we are comparing currently, this is the Ragon plot. So comparing hydrogen, we are trying to see if hydrogen can compete with the likes of diesel or gasoline. So we are currently in this case here. So hopefully with the new technologies, we can increase the volumetric density and also the volumetric density per liter, and also for the hydrogen. So it can be used and more economical, so it can be used for mass production as well. Thank you very much. If you need to contact me, this is my email, and then you can find more about what we do at KAMES and our KAMES website here. Thank you very much, and I think we can answer some questions for now.
Yeah. Later for Q&A session. Yeah. Okay. Thank you, Dr.
Okay, sorry.
Yeah.
Thank you very much.
Thank you, Dr. Hanif, for providing us this very interesting presentation about catalyzing sustainable hydrogen energy, about the production and the storage. And also thank you for sharing us about blue hydrogen and green hydrogen as well. It seems we have some questions from the audience in the chat box. However, we save it and cover it later in the Q&A session. Ladies and gentlemen, you kindly to submit questions to our speakers by typing them into the chat box, or you may ask directly next in the Q&A session by click raise hand button. And then we are now moving on to the fourth speaker. Now let's please welcome Dr. Apip Amrullah. Time is yours.
Okay. Thank you very much. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Sorry, please allow me to close because my of the device for the camera, so I cannot open the camera. I'm so sorry.
It's okay, Doctor.
Okay. Let me share my screen first. Oops. Sorry. Okay. Okay. You can see my screen. Is it okay?
Yes, Doctor.
Okay, thank you very much. Okay, let me start that. Assalamualaikum warahmatullahi wabarakatuh. Good morning, everyone. Thanks to the committee for the fruitful webinar in this morning. Thank to Dr. M.U.C. Ernawati as a worthy from this program, which is the world-class professor, and my deepest respect to the wonderful speaker here. Thank you for all the speaker. There is the Professor Renewable from the University of Tsukuba, and then there is Professor Muhammad Aziz. Assalamualaikum, Prof. Aziz. And then Dr. Abdul Hanif Muhammad from Deputy of Director of the Center of Material and Energy Science, University Brunei Darussalam, and also the Dr. Eng Panji Prawisuda from the New and Renewable Energy Research Institut Teknologi Bandung. In this morning, I would like to talk about the energy, sustainability, and locally resources for bioenergy production. Actually, in this topic, I will not talk much about the sustainability because the previous presenter already explained in detail about the sustainability and also about the energy. But in this term, I would like to share our finding for the how to use the local resources for the bioenergy products themselves. Okay, if we're talking about the energy, is actually this cannot be to separate from the sustainable development goal, as mentioned by Professor Aziz. The Sustainable Development Goal or the Global Goal are the collective of the 17 interrelated global goals designed to be the blueprint achieve a better and more sustainable future for all. Actually, as we know that the SDGs as is were set up in 2015, and then we will achieve the product in 2030. And then the another one is here. This is important thing is we're talking about the energy, which is the SDGs is the point in the point 7, which is the affordable and the clean energy, with the encouraging the sign that energy is becoming more sustainable and widely available. And then therefore that renewable energy is making impressive gains in the electricity sector, as mentioned from the previous presenter, because they are using the hydrogen or something else for the energy for electricity. Okay. And then this is the triangle for the sustainable development purpose. As I also already mentioned before, that the sustainable development is one of things that decided to improve the worldwide standard of living while considering the effect of the economic is mean that the sustainable development is not have to link each other for the environmental, economic, and social, including the demand of something else. Okay. If we're talking about the contribution of the bioenergy, the bioenergy plays a role in the 3 main energy uses sector, which is the heat and also that including the cooling and electricity and the transport. Then the contribution of the bioenergy, and the contribution of the bioenergy itself to final energy demand for heat or traditional and modern for outweighs its use in either electricity or the transport. We can see here that the biomass is 40% as a source for replacing the fossil fuel. This is the 40% of the biomass can be used as the electricity, which is the 0.4%, sorry, and then transport is 0.8%. Then the heat, building and tradition is around 9%. It means that the biomass is the bit of potential for the replacing the fossil fuel to making the alternative sources for the energy in the future. And then if it's talking about the biomass actually or the energy consumption, actually this is the in Indonesia that's the many have the policy and regulation, but this is some kind of the policy and the regulation from the Indonesia. For example, this is law number 30/2007 is focusing on the energy, which is the priorities to display and utilization for renewable energy. So it means that if we concern about the renewable energy in Indonesia, it's already mentioned, it's already have the based on the regulation. And then if we're talking about the biomass, it's more interesting if we should to know that what kind of potential biomass it can be used for the bioenergy, especially for Indonesia. It means that we have the many kind of the biomass in Indonesia. So here show that the table about the kind of the biomass is a bit the kind of the biomass such as the rubber wood, logging residues, so timber residue, polywood, sugar residue, something, and then coconut shell and palm oil residue. If you can see here, the production is a bit higher. It means that we have the big opportunities to use the kind of the biomass to making the another bioenergy sources. Okay. So why biomass? Because the biomass is based on carbon, and then also the biomass is the environmental friendly and the low energy consumption. Then also the reduction waste and pollution is they have the effect on the environmental, and also they provide an opportunity to elaborate novel high performance. Also we can make the biocompatible. As also it's already mentioned, but the biomass is the actually this is the all the the story, because the biomass is, but the biomass has the as the information that we need to improve. We need to improve, and we need to elaborate more and for the future, because the biomass is most interesting to concern for the in the future. So in this study, in this presentation today, I would like to share our finding for the using the local resources to making the another bioenergy for the future fuel. So as we know that the formation of the carbon here, this is actually has the three phase for the formation of the carbon from the biomass, which is the gas phase and also the liquid phase and the solid phase. You can see here that the gas phase can be reaction under similar condition from the very wide variety is carbon containing gases. That the containing gases actually including the carbon monoxide, methane, and then something else, the carbon dioxide. And also the liquid phase is reaction using the thermoplasmatic polymer, and also then another such as bituminous pore and synthetic polymers and such as the polyphenol chloride. And then we can see for the solid phase, it can be used as the carbon fermentation process in the solid phase. Then all of the product can be used another to be fuel something else, and including the liquid fuel or also the solid fuel. Okay, if you can see the classification of the biomass here, we can see based on the categories here to divide it into categories, which is the cultivated crop and the waste material. In Indonesia also we can find all of them, actually almost all of them we can find in Indonesia. For example, this is the sugarcane, and then also the casapas with potato and something else. Eucalyptus also we have the much in Indonesia, so it means that we can it's not rare to get the feedstock in Indonesia if we concentrate about the biomass. In aquatic plant, including the microorganism, by including the chlorella or something else, or the macroalgae or something else in Indonesia, is very easy to find it. And then the second category, which is the waste material, which is the agriculture, including the fishery and the forestry. Agriculture waste, including rice husk, rice straw, and the straw, etc., is pretty easy to find in Indonesia also. Then in case of the waste, industry or the domestic cases, including the sludge and something else, is huge in Indonesia. So it means that we need to move to in the future to use all of the material can be produced in Indonesia to making the another alternative source for the energy, renewable energy. So as I mentioned before, that we focus on the biomass. Actually, in Indonesia, especially in Indonesia here, that biomass can be divided into two, which is the non-wood and also wood. We consider about the wood biomass. Actually, the non-wood can be divided to grass, leaf, seed, fruit, and something else. And then also the wood is hardwood and the softwood. Okay. Here, that's kind of the biomass you can find in Indonesia also. There's so many things it can be. Actually, the waste is also including biomass also. Then we can use waste as a source of energy alternative in the future. There is some kind of the many researchers have find out about the waste to compared to the waste to into the fuel. Okay, this I want to skip and want to making for the biomass technology. Here, if we're talking about the biomass, so we need to know that how about the technologies can be used for the convert the biomass into the another product such as the liquid fuel, solid fuel, and the gas fuel. The common technology, we can see here that the thermal technology, we can divide it into four technology, which is the thermal compression technology, mechanical and thermal compression technology, and thermochemical compression technology, and also biochemical compression technology. For this technology actually depend on the raw material that can be used in this product. And then to produce the another product, if we were talking about the liquid product, actually some thermochemical compression technology can be used, such as the pyrolysis here. So from the pyrolysis, we can process the liquid fuel. And then in the features, in the next slide, I show you that another research for biomass, it can be used for the liquid fuel, and already published to another international journal also that this is working on the pyrolysis and gasification. And then for the thermal compression technology is like the direct combustion. Is mean that the biomass can be used directly into the direct combustion actually, but there is some effect for the environmental, which is they can be making the pollution, for air pollution and something else. And then for the mechanical and thermal compression technology, including the preparation and drying, it can be used for the refuse dry fuel, then can make a solid fuel for the combustion and thermal energy. And for biochemical, including the fermentation and aerobic digestion for making the biogas, actually for the gas fuel, and also ethanol for the liquid fuel. For the actually the goal is for the combustion. And we're talking about the biomass also. It's not be can be it's still correlated with the energy. So it means that a lot of the sources for biomass energy in Indonesia is mean that we have the big opportunity to use the biomass as replacement for the fossil fuel. So it means that we need to improve our idea and then our technology to make it easy to get the alternative sources for the energy in the future. Okay, best for the primary energy mix target by 2025. Here we can see that the renewable energy should be 70% is already used, including the biofuel, geothermal, and other renewable energy and co-liquefaction. As I mentioned before, that the biomass has a big potential for the renewable energy, but there is something effect for the economic, because the renewable energy actually is mentioned before that it cannot be making the big industry for making easy to make a big industry to make the, for example, the power plant something else. But also in the future, maybe 10 or 20 years in the future, we will have the effect for the when we use the biomass as the source for the energy, and because the biomass can be obtained well, and then it's continuously characteristic for the biomass. Okay, here, so I show you that the kind of the biomass based on the generation. The first one is the first generation edible biomass, such as sugar beet, sugar cane, wheat, and corn, something else. And then the second generation is non-edible biomass, including the woods, so grass and waste. And then third generation is including the alga biomass, which is the macroalga or microalga, and then fourth biomass generation is including this will be focused on the process cooking, including the pyrolysis, solar to fuel generate a alga gasification or something else. And then this in the figure here we can see that we can the product, if we have to use the another technology such as the gasification, liquefaction, pyrolysis, and combustion. It's actually all of the product, it can be used for the energy, electricity, or something else. And then the different technology should be the different product. For example, the gasification here, this can be produced the same syngas, and the liquefaction, it can be produced by oil, and also pyrolysis can be produced syngas and by oil and biochar. Then direct combustion should be for the electricity. All of them is actually for the electricity can be used, it's easier. But the process is not easier that we need to be thinking about the how to get the process more easier than other process. Okay, this is as I mentioned that the characteristic of the biomass is based on the to making the product is easier to make based on the characteristics such as the wet biomass, solid biomass, and sugar, starch, and fat, and oil fat. This is like the first generation, the second generation, third generation, and the fourth generation. This is the different product for other generation. Then in the for using the local energy sources, it's not only fuel we can get from the biomass, but also is the interestingly that this we can get the another product such as the chemical product from the another side from the biomass. We can use the, for example, here they use the biomass as we know that this contain more of the cellulose, semicellulose, and lignin, and they use the catalytic to get the some of biofuel, or in the biofuel actually in the liquid fuel we can get the another compound of the chemical, for example maybe phosphorus, something else, or methanol or something else. And then the biochar can be used as the activated carbon or carbon nano. We can get the activated carbon for air catalyst or something, and maybe we can do it for the absorbent also. So it means that if we use the biomass, we can get more product, not including only the fuel, but also that we can get another chemical compound. Okay, this is the some process to get the liquid fuel from the local energy sources. This is coconut shell is produced from to make for the feedstock in the process of pyrolysis, and then we can get the charcoal and biochar, and also the bio oil. In this pyrolysis process, we can see that three of product it can be used for the energy. The goal is it can be used for energy. For example, charcoal here can be used for fuel, activated carbon, raw material, something else. And then the biochar can be used for the soil additive or absorbent material. And also the bio oil can be used as fuel and chemical. Then the last one, all of them can be used for the energy. From the pyrolysis process is the bio oil can be improved. The quality can be improved by the upgrading process, which is for example here the distillation, simple distillation process. So from this distillation process here, this is the feedstock in the process of the pyrolysis, and then the bio oils can obtain from the local energy sources, such as the coconut shell. By the simple distillation process, we can improve the quality of the oil, and then we can see here the result from the bio oil process. The raw material it can be look like the more clean from after the distillation process. And then about the characteristic for the liquid fuel, then from the pyrolysis process, we can see that most of them have contain the acetic acid and also the propane and also the phenol. When we use the pyrolysis at the temperature 500 degrees C here, the phenol is around 31% based on the GC result. But also when we try to improve the quality by distillation, simple distillation process, the phenol is most increasing from the 31 into the around the 30 or 40 something, around the 38 or approximately 40% based on the product. And also the acetic acid increasing, and also the phenol based on the result is decreasing because there is consumption to to produce the phenol and acetic acid. So it means that by using the local resources for biomass, is had the effect. I mean that have the economic value if we concern about the how to making it more visible to the making of the fuel. So it means local energy resources. We have the many things. So we need to more improve our idea and also the technology to get the something else from the local resources for the renewable energy to make a bio energy. The another resource, the local resourcing, which is the Puruntikus. This is the like the grass is collected from the Kalimantan. The Puruntikus is like the is can be grown in the wet area. So it means that it's like this can be disturbed the another plant when the Puruntikus is grown in the another plant itself. Then we use the Puruntikus here by the pyrolysis with the temperature of the 300 to 500, and then we get the phenol in the liquid phase. So from the process of pyrolysis of the Puruntikus, it means that we can create the bio oil product, mainly composed of the phenol, acetic acid, and also the purpura. It means that we have the big challenge, the how to recover phenol from the Puruntikus. So it means Puruntikus is not only like a grass, but also it have the potential for the liquid fuel or bioenergy in the future. We need to improve all of the technology or the idea or something to find out the how did we can recover the phenol from the Puruntikus. Okay. Here I saw that the another thermochemical process, which is the gasification, is from the local resources such as the waste from the household, which is the sewage sludge. This can be used as the can be converted by the gasification process. Actually, we can get the syngas and also to produce the gaseous fuel. But the another opportunities we can get from the waste of the household. We can use the for the solid fuel, which is the by the hydrothermal treatment. Also, then we can also making the some technology, the novel technology, which is the supercritical water gasification technology, by requiring the high temperature and high pressure. And then interestingly, in the sewage sludge, not only solid fuel we can get it, but also that the another gas, and also the another in the liquid fuel, in the liquid product, we can get some interesting chemical compounds such as the inorganic phosphorus and also the organic phosphorus. The organic phosphorus itself can be used for the fertilizer. It's very good for fertilizer, as we know that fertilizer can be effective for the growth of some plant or something else. Then from the sewage sludge, by the supercritical water gasification, here we can recovery the sewage. We can do recovery of the phosphorus, organic phosphorus in the liquid phase into from the organic phosphorus into inorganic phosphorus to making the some resources for the fertilizer. So it means that not only gas, as I mentioned before, not only gas or the liquid fuel, but also we can get the another products such as the phosphorus for the fertilizer. So we introduced the supercritical water gasification in this result. So based on this result, around 80% the phosphorus can be recovered from the liquid phase. Here, that the supercritical water gasification is not only gas but also the solvent for organic matter. Then also reaction for the hydrogen gas production. We can see here the process for the sewage sludge as the waste from the household. by the supercritical water gasification, the reaction can be taking place in the short time, and also just only the water. So this is the advantageous when we can use the supercritical water gasification to produce the products such as the gas, liquid product, and something a chemical compound. And then from the supercritical water gasification process, we cannot produce the solid because all of the solids can be converted into the gas and the liquid. And also we can use the wet biomass to directly using the supercritical water gasification, because we no need to dry it before. So it's mean that the in case of the economic value, is supercritical water gasification is more applicable, is more economic applicability from the another process is best for our knowledge. And also the supercritical water gasification require the high temperature, but also the temperature, the heat can be recovered by the heat exchanger of more than 80%. So it means that energy should be minimum, can be lost. The energy loss should be can be minimum in this process. And then the another result should be hydrothermal carbonization, as mentioned before, that the hydrothermal carbonization can be produced hydrochar and bio oil. Bio oil can be produced, can be used for the biofuel, and also the hydrochar is a soil conditioner, and also the manure then can be used as absorbent from the wastewater treatment plant. Okay, the another biomass also can be produced for the pyrolysis process, which is the rice husk. This is the locally sourced from the biomass in Indonesia. Also, we have the much of the rice husk in Indonesia. Everywhere we can find it. It means that by using the biomass, for example, rice husk, and using the thermal conversion technology, which is the pyrolysis, we can obtain the as I mentioned, like the liquid fuel or something else for the solid fuel. Okay. If you're talking about the biochar and hydrochar, it can be produced from the pyrolysis. The biochar and hydrochar can be application for the absorbent, and also that the pressure for the catalyst, and then the cell admendant, and also additive for anaerobic digestion or composting electrochemical energy storage. So that is the problem. There is no problem. I mean that all of the product can be used from the if we treated the biomass by the technology, including the thermochemical compression or anaerobic decompression technology. Okay, this is the characteristic of the activic activic carbon, and something we compare with the biochar and charcoal. And then also this is the another sources is can be used for the for the making the bioenergy production. Actually, here we show you that this is our collaborative issue with the international collaboration with the title of the high value chemical and syngas production from Indonesian marine macroalgae. So macroalgae or microalgae can be used as for the product as for the energy, including the syngas or the liquid fuel. And also the chemical compound from the marine macroalgae by using the different technology, which is including the supercritical water gasification to process syngas for the energy or the future energy. Here, then also we can use for the biogas also, and syngas from the macroalgae, including the biogas from the macroalgae. We try to making the different for the FUEN, which is the deionized water and saline water. We can see here that the produce for the methane really different between the ionized water and the saline water. So it means that by differences of the technology or differences treatment should be have the another resources. The conclusion that all of the sources we have the more local sources for the biomass, and then also all of the sources is can be produced through the making the another alternative sources for alternative fuel in the future. Depend on the technology and the depend of the characteristics of the biomass can be we can use for the raw material. And then the future plan that in our future plan, which is we will use the eucalyptus biomass and the biological temperature to making the to produce the bioenergy, including the bio oil, biochar, and the gases by the pyrolysis and the gasification. And it's mean that the thermochemical conversion technology in this case is more reliably for the compared to the such as the eucalyptic biomass into the energy sources. And then also making the kinetic reaction for the pyrolysis is to find the optimal reaction pathway, then propose the high efficiency for the bioenergy sources. Then the last one here that is more important things is making the concern about the life cycle assessment. The life cycle assessment, as we know, that the tool to assess the environmental impact for the product, process, or activity throughout its life is the cycle we conduct in the next year. So this our purpose, our future plan for the our laboratory to making the more to improvement the using the local resources for the biomass to produce the bioenergy. And then the last one here that is successfully for the sustainable development is must consider about the steep perspective, which is the social, technology, economic, environmental, and political. As mentioned before, that technology should be the should be the absolute. I mean that is based on the technology to making the something product, and also that social should be should be have the more should be give the our chance to making the some technology to improve the technology to produce the product for the future, and also to the product is can be has the connectivity for the economic and environmental, and also the political should be support our the idea or technology can be developed in the future. Okay, I think that's all my presentation, and thank you for all the participants. So I will back to the moderator. Thank you very much.
Thank you for that amazing presentation, Dr. Apip Amrullah. Dr. Apip tell us about energy, sustainability, and local resources for bioenergy production, and he tells us about his research results also about utilization of several potential local energy resources. Ladies and gentlemen, then we are now moving on to the fifth speaker, which is our last keynote speaker for today's webinar. Let's please welcome Dr. Panji Prawisuda. Time is yours.
Good morning.
Good morning, Dr. Panji.
It's really good to see Ms. Musharrafah. I thank you, and I also thank Professor and also Bu Lucy for so that there's also my senior here, Pak Muhammad Aziz, also coming to this event. I think most of the topic will be covered by him, not by me. So I will be the last here. Thank you very much for the chance. Currently in TPA Jatibarang, so unfortunately it will be quite maybe a little bit noisy. So I hope it will not disturb my voice and also my presentation today. I think I still haven't got the permission to share my screen.
the committee, please can help Dr. Panji to give permission to share the presentation.
Okay, all right.
Okay.
Okay. Is it visible right now?
Yes, Dr. Panji, we can see it.
All right. Okay. Thank you very much. Let me use myself. My name is the New and Renewable Energy Research Center of ITB, and I also act as the research coordinator in the Faculty of Mechanical and Aerospace Engineering. So today I would like to share about our small research. It's entitled From Waste to Earth, Utilizing the Unutilized Resources Using Hydro, Thermal, and Mechanical Technology. So maybe heard about this before, but I would like to explain why we need the business as usual case, but in the new technology case. And why is that? Because of the change of waste. I start with the picture colonial typical residential in Indonesia back in 1980s, and the third picture is the residential area in Indonesia in 21st century. So what I want to show you is not about the house, but about the garbage can. As you can see here, many people has already changed their method of treating the waste. First of all, in the Dutch colonial period, people are throwing it inside a big can or a big basket. But people make their own house of the owner of the house. Nowadays, we are going to practicality. So many people like to throw their waste inside the plastic bag, inside the garbage bag, and they just put it on the fence or on the tree. So in some time, maybe we can see that these trees are having a fruit of waste. And this change of behavior, change of lifestyle, also making a change of waste composition in Indonesia. If we compare in this table between the year of 1988 and the year of 2006 and 2010, we can see that the composition of the waste has already changed. What I want to underline is the organic waste mostly from the food waste. It already reduced from 77% to 68% in 2010. On the other hand, plastic waste is increasing from 5.6% up to 12.4%, more than twice of those plastic composition in 1988. And what does it lead us? Take a look on we can see that typically in Indonesia we have the organic waste of about 55%. But in the fraction of volume, we can see that it merely fill about 17% of the overall volume of the waste. And this is in the opposite with the recyclable plastic. For the recyclable plastic, the mass fraction is only 10%, but the volume fraction is almost a third of the total waste volume. So that means in the beginning of 21st century and nowadays, we will see more and more plastic, not in the term of mass, but in the term of volume. However, what we do towards this changing of waste is still the same. We still collect the waste, we still transport the waste, and then we just dump the waste. I give you one example of the waste dump in my city, in Bandung. The distance between the Bandung City Hall and the landfill is about 42 kilometers. So that means the waste truck, the garbage truck, must transport the waste for 42 kilometers before they return back to Bandung City for the same distance. That means this truck carry the waste for the total transportation length of 84 kilometers. That means we will have skyrocketing fuel cost in the future because the others considerably far than the current waste. So this leads us to one. I ask our that the question about we can conflict, but I want to underline that waste here showing the kilocalorie per.
Sorry, ladies and gentlemen, I think Dr. Panji is out of this meeting. Maybe Dr. Lucy can call Dr. Panji to join us again.
Okay.
Okay.
Wait.
Okay.
Ms. Sharofah, can you
Yeah.
hear my voice?
Yeah, Dr. Panji, please go. Yeah.
Yeah, it's a side problem. We don't have enough.
Yeah, it's okay.
Let me share my screen.
Yeah, you can continue your presentation.
Okay. So if we compare the heating value of waste compared to that of coal of about 5,000 kilocalories per kilogram, we can see that actually some part of the waste are having twice that of the heating value. That means, let's say about, let's take a look on the polyethylene, for example. Polyethylene is about 11,000. That means theoretically, one kilogram of coal is having the same amount of energy with half kilogram of polyethylene. However, the density of polyethylene is so small, so light that we have a problem with feeding. It's another problem. But in the term of energy, yes, waste has energy and waste is energy. And not just the daily waste from the garbage, but also from the agricultural waste. These are the compiled results from the Agricultural Ministry of Indonesia in 2018. You can see here from the oil palm industry, we have plenty of biomasses to be as potential as the energy sources. Also with the rice, we can see that the biomass waste from the rice plantation, mostly in Java, and also some part in Sulawesi is also having a high potential of energy. So this is actually possible for us to use. If we compare between the rice, corn, cassava, oil palm, we can see from this figure that the amount of total residue from the crops is about 50 million ton per year for rice and about 65 million ton per year for oil palm. We have plenty of waste here. And as long as human exists, we believe that it will be. So the solution of waste to energy is quite reasonable, quite logical to have the alternative waste treatment and also to have the alternative energy source. And if we calculate in simple term for several cities in Indonesia with different amount of waste per day, we can see that with the assumption of only about 5 megajoule per kilogram heating value of waste and also only about 25% of energy conversion efficiency to electricity, we can have approximately about 81 megawatt of electricity in Jakarta, about 22 megawatt of electricity in Bandung, 29, 36 in Bali, and also about 25 megawatts in Medan. It's quite adequate energy resources. And if we compare it with the biomass, we can see that up to 700 megawatt of energy can be generated in West Java only from rice husk and rice. You can see from this figure here. Now, many people think that waste to energy is against the 3R, against the reduce, reuse, and recycle. Of course, if we take a look on the waste management hierarchy, we can see that the most favorite option is reduce, and afterwards it's reuse, recycle, and then after that we can start to do the recovery and landfilling. However, if I draw a line here, separate between the 3R and also the waste energy, we can see that the 3R is effective for the future waste. While the WT is effective for the current waste. So it's actually working on direct burning from the burning, or we can use the methane from the anaerobic digestion of the waste, and we can use this landfill gas to turn on the power plant. But Indonesia also
Dr. Panji? Dr. Panji? Can you hear me, Dr. Panji? Okay, maybe I can type. Okay. I think Dr. Panji is out of room again.
Oh. Signal is not clear.
Okay.
How many minutes do I have left, Ms. Musharraf?
2 minutes more.
2 minutes more.
Yeah.
So, really sorry for that. I will need to skip this part. Mostly, I want to show you what we develop in the laboratory. So, let me skip to this. We have a lot of challenges for the waste, especially for the moisture content, for the chemical, and for the ash content of the waste. So then we have to prepare some technology to treat the waste so it can be used as solid fuel. So in our laboratory, we developed several technologies like Dr. Afif already explained. Also, we have these processes of what's so-called hydrothermal process. We call it wet process or wet torrefaction process. And we also have the dry process for the dry torrefaction and also for drying. This is what we are doing for the drying process. We are using today's bed dryer using superheated steam to reduce the moisture content of the waste and also to increase the carbon content of the waste for some part. So in that way, we can have a higher heating value of waste only by drying. And also we have this dry torrefaction process in our laboratory to increase the carbon content. And this is what I focus more on the wet torrefaction or hydrothermal process. And I think you have already heard it from Rapid. I don't think I need to explain it further, except if there is a question. So our target is to produce solid fuel. It's a little bit different from what Dr. Apip explaining, I think, because we want to use as low temperature as possible and as low pressure as possible. So the reactor itself can be produced and it can be used in higher scale because we don't need very high pressure, we don't need very high temperature, and we can make it inside Indonesia. So these are what we can obtain from the waste. I think we usually make some experiment, soft and mushy product, but the plastic will be agglomerated and it can be separated apart from the organic waste. So these are another feature of the hydrothermal process itself. We can separate the aluminum from laminated plastic. I think this is our big problem for the multi-layer plastic because it has the plastic packaging. So by hydrothermal process, we can separate this and we can have the pure plastic and pure aluminum. Maybe I want to show you the last picture of our reactor. Okay. So we have already designed and also produced some reactors starting from small one, 1 liter for the household, until the biggest one is the maximum of 2 tons per day. These are static reactor. These are picture. You can see from the of hydrothermal waste and
Dr. Panji? I think Dr. Panji left the meeting. Bu Lucy, can you help me to
Yeah,
call Dr. Panji again?
Yeah, Bapak.
Okay.
I think Dr. Panji has trouble in his
Network.
internet connection. Yes.
Yeah. Yeah, we can wait a minute.
really sorry I got disconnected.
It's okay, Dr. Panji.
Ms. Musharrafah, I think
Yeah.
that wrap up the presentation. I hope
Oh,
it will
it's that's
not
all.
be a big disturbance. So I will also
Yes, Dr. Panji. Dr. Panji.
I will close the presentation.
Oh,
Thank you.
okay.
I think
Okay.
yes. I think
Thank you, Dr. Panji, for providing us this very interesting presentation about how.
so yeah.
Yeah. Oh, sorry. Yes, Dr. Panji. Oh, okay. Okay, Dr. Panji, thank you for providing us this very interesting presentation about how to change waste to energy source. Okay, ladies and gentlemen, our all speakers have delivered their presentation. If I can come to a general conclusion that we all agree to create clean and renewable energy sources. Our speakers also have presented several examples of sources that we can utilize, including biomass, hydrogen source, waste, and etc. And then our speakers also deliver the strategies to be pursued to achieve clean energy technologies for sustainable development. Thank you, Prof. Enomai, Prof. Aziz, Dr. Hanif, Dr. Panji, and Dr. Apip. We are now going to begin answering the question. It seems in the chat box we have several questions for all our speakers. The first question is coming from Dr. Lucy Arnawati. This question for Dr. Hanif. Please kindly, Dr. Hanif, to give his insight to this second question. Sorry, two questions. The first one is, how much energy does it take usually for making 1 kilogram of hydrogen? And the second question is, among the numerous methods, what is the cheapest way to produce hydrogen? Thank you very much, Hanif. Please kindly give your insight.
Thank you very much, Moderator Musharrafah. So it's a good question. So currently, the standard that we are trying to beat is still steam reforming, because the technology is matured. It's been used for almost 100 years in the gas downstream process. For example, people producing urea, people producing ammonia, and also people producing methane is still using steam reforming reactions. So there's not much. So it depends on the efficiency of each plant as well. But typically, there's no there's no real number, there's no actual number that because it depends on the efficiency. But as you know, the steam reforming, and also it depends on the setup of different plants as well, because some people can produce, does it using a higher pressure or a higher temperature. But currently the best efficiency is around maybe 80% of the plant. So that makes it quite the most economical as well. So if you think about dollars per kilogram of hydrogen, people are reporting it to $1 to $2 dollars of per kilogram of hydrogen production. But as it doesn't, but as the water splitting technologies have gone so much recent developments, it's getting close to that. So we are getting close to the $1 or $3 mark per kilogram. But also you can see right now in Europe, it all depends also because of the gas prices. So currently, as I told you, mostly all hydrogen is produced by, nearly all hydrogen in industry is produced by steam reforming process. But currently, if you see in Europe, most of these steam reforming plants, they are closed because of the high gas prices now. So it depends on the gas price as well. But we are, it's still the cheapest, but again, it varies in terms of the efficiency and also the plant setup and also the gas price. Thank you. I hope that answers the question.
Yeah, thank you, Dr. Hanif. The next question is coming from Dr. Diga from University of Palangkaraya. There is question for Professor Enomai. Prof. Enomai, please kindly tell us more about the sources of the vibration from the electric generator that has been applied in the poster, and what are the future challenges in the development of electricity generators from vapor vibration. Professor Enomai?
Yes.
Yeah.
Thank you for the question. So about the question is
the source of the vibration from the electric generator. Yeah.
A poster. The application to poster is possible, I think. So original idea is to activate the poster using the sound or noise around the poster. That's why small type of power generator from the vibration set backside of the poster, and then if the surrounding is noisy and like in streets of the station, crowded station, for example, it's possible, I think. But the moving something, some object needs a lot of energy. That's why maybe to light LED light or low energy consumption devices can be attached to the poster.
Okay. And the second one, what are the future challenges in the development of electricity generators from vapor vibration? Challenges.
So unfortunately, the amount of power sourced from the sound or noise is not so large. That's why. So we have to. So we have to look for the appropriate places to for something that works at a low energy consumption.
Okay, thank you, Professor Enomai. And then for Professor Aziz from Dr. Dirga, excellent presentation, Professor Aziz. From your point of view, co-firing with biomass program can work in Indonesia, and then converting biomass to electricity, then to hydrogen, and back to electricity be more efficient for reduction of emission CO2, or do we need multiple inputs from renewable energy to produce hydrogen? Please, Prof. Aziz.
Okay, thank you very much for very nice questions. The first point is related to the co-firing or co-combustion technology, actually. I think in this case, actually, for the co-combustion, we have two options. The first is that we co-combust the hydrogens, or the second method is that we co-combust with ammonia. Ammonia is also one of hydrogen's carrier in this case. So it means that I think co-firing or co-combustions of ammonia to the existing coal-fired power plants in Indonesia is also quite promising. And it also, actually, I have also discussions with the Ministry of Energy and Minerals, actually, ESDM, I think. They are also planning, because there's one company also from Japan, Mitsubishi Heavy Industries also. They are trying to have any kind of demonstration also in Indonesia for co-firings of ammonia to the existing coal power plants, actually. And in terms of technology, it is really feasible. Because we know that both coals and also ammonia has quite similar lower heating values. So it means that combining or blending these two different fuels actually are also quite promising. The problem is that, based on several projects also, especially in Japan. Actually, in Japan also, we have also 3 different projects for co-firings or co-combustions of ammonia to the existing coal power plants, actually. Creepy, Chuo Electric Power, and also I think Ishikawa Heavy Industries, IHR, they have conducted any demonstration plans and demonstrations projects, actually. And the result is that regarding the NOx emissions, okay, based on, it really depends on the conditions that we feed the ammonia during the co-combustions. Based on the result conducted by CREPI in Japan, actually, in case that we don't blend together the fuels from very beginning, so we don't premix the fuels itself, and we put, or we feed the ammonia after the combustion, after the coal nozzle. So it is quite I think it's the distance between the burners can be more or longer. It also potential to reduce the NOx. But in case that we premix the fuels, and this demonstration has been conducted by Ishikawa Heavy Industries, there's any increase of NOx emissions in the exhaust gas. But actually, as they try to increase the ratio of the ammonia to about 20%, the increase of the NOx itself is below 20%. So based on this result, actually, they said that this kind of co-combustions of ammonia and coal, in terms of emissions, NOx emission especially, it is also quite feasible. That's the technology that we are still currently doing with that. And also correlated with whether it is quite feasible for Indonesian case or not, I think yes, because Indonesia also quite, we have large scale ammonia productions also. We have, basically it is produced from methane or natural gas. But actually we have established technology for ammonia synthesis based on Haber-Bosch process. So I think this kind of co-firings also, as I mentioned previously in the roadmap, starting from export-oriented market, and then we can start from the large-scale co-combustion technology. So in these terms, we can start for the pilot demonstrations for combustions of ammonia to the existing coal power plant, actually. And the second question is correlated to the converting biomass to electricity to hydrogens, and then hydrogens to electricity. It means that this kind of routes is also very inefficient. Okay, so in general, we should set up any kind of strategy how to efficiently convert the fuels or the feedstock itself. So I think in this case, converting biomass to electricity and electricity to hydrogen and then back hydrogen to electricity is not so efficient. Our target, mean target, however, in our energy system, basically the electricity will be the base. Because what? Because the convenience, because it is efficiency actually. So how we can utilize this kind of biomass? Okay, biomass can be converted to electricity in case that there is any kind of surplus electricity. And basically this kind of surplus electricity maybe comes not from the biomass itself, but it comes from any other more fluctuating resources, including solar, including winds or etc. So in these terms, usually we convert this kind of fluctuating ones or any kind of surplus electricity then to hydrogen. So not from very beginning, we just convert the biomass to electricity to hydrogen and then back hydrogen to electricity. No, but we should have any kind of scenario. We are not converting directly from biomass, but we are converting the surplus electricity. So it means that rather than the electricity is wasted or exhausted or abundant anyway, it means that it is really better to utilize this kind of surplus electricity or unutilized electricity to hydrogen, and then hydrogens to be converted back to electricity. Although the total efficiency is low, but it is really better rather than we just abandon or waste the electricity. Thank you very much.
Thank you, Professor Aziz, for nice explanation. And then the next question for Dr. Hanif, or maybe also for Professor Aziz, talking about hydrogen as one of renewable energy source. As we knew that the problem of green hydrogen currently costs 3 times as much as natural gas, and the producing green hydrogen is much more expensive than producing blue hydrogen because electrolysis is expensive. Although the price of electrolyzer are coming down as manufacturing scales up, then from your perspective, what is the best way or strategies that probably able to bringing down the price of green hydrogen so that more people can produce or even will buy it? Thank you very much. Maybe Dr. Hanif and Professor Aziz can give your insight.
All right, thank you very much. So of course, currently we're still, but at the current, we can't compare it as a static comparison because it's always a dynamic comparison. At the moment, like for example, like in Europe, where they're facing winters currently, where they're facing problems that there's not enough energy because gas prices are quite expensive now. So that's no longer the case where electrolyzers are quite expensive. But as if you look into the longer trend, then when we reach more technological maturity, so we will have in terms of, and of course, we don't know how stable the gas prices or the oil and gas prices, but it will always shift towards this coal, gas, and oil. But then again, this is only due to supply, demand, and also who has the oil prices, which is controlled by political events and things like that. So at the end, as I think Prof. Aziz can explain this later on, especially the triangle when we have, when we also need to see economic viability, but also the security as well. So for example, like for us, having the water splitting will give us an extra option in case there's no gas or oil anymore, for example. But I'll leave to Prof. Aziz to explain further. Thank you.
Okay, thank you, Dr. Hanif. How about you, Professor Aziz? Please kindly your...
Yeah, thank you very much, Dr. Hanif. Very, very good explanations, actually. And
Professor Aziz?
This case, I think, in total, when we are dealing with any kind of hydrogen, we are facing several problems: productions, storage, transportations, and also utilizations. Okay, so it means that when we would like to reduce the total cost of the hydrogen, it means that we should reduce each total cost cost of the total process, okay, for the productions, okay, and also for the transportation and storage. It is very important also. The problem is that related to the storage transportations is also the biggest one. Although we can produce the hydrogen like in Japan's NEDO scenario, the price of the hydrogen itself is about, okay, maybe about 10 yen per cubic meter, something actually. But the problem is that with the transportations can cost about minimally same with the productions, or it can double or triple. So that's the problems. So how far we can really create any kind of market to store and also to transport the hydrogens in massive amount, a large scale. So what we would like to do is that, and this is also the big projects in Japan actually, converting the coals in the Australia and to hydrogens, and hydrogen is liquefied to liquid hydrogens, or maybe it can be converted to ammonia, and then this kind of liquid hydrogens and also ammonia is brought to Japan. And we would like to measure whether this kind of methods in case of large scales production and also transportations is really feasible in terms of economic point of view. And also that's the total cost. And for the utilizations and how far we can have strategy or scenario to utilize hydrogen wisely, it's also very challenging. Now we are, as I mentioned also previously, if we just use hydrogens for electricity generations, and this kind of electricity is only sold or only supplied for supplying any kind of base load power. So it means that the price itself is very low. It means that it is the quantity market. The quantity market usually like in a Indonesian market, maybe I think it's about 1,000 rupiah per kilowatt hours. But like in European market, when I joined a project in Denmark, what they have is that they distinguish between the quantity and also the quality market. The quantity market, okay, we supply the electricity in terms of kilowatt hours. But when we would like to supply in terms of the balancing, ancillary, or any kind of premium services, the price itself is really fluctuating, and it can reach about 100 times of the quantity market. So in this case, we would like to provide to use the hydrogen itself for the adjusting generators. So that's why we can sell the electricity produced from the hydrogens with any kind of premium price, not only with the base price for the electricity itself. Because what? Because we provide with any kind of services, quality services. And also the second point is that now we need any kind of market reformations. Now currently we are still projecting that in our market, we have that, okay, solar, wind, they enjoy any kind of FIT, they enjoy any kind of high price of electricity. Yes. But as the future trends, this kind of solar and also winds, the price of the electricity will be the lowest. Because what? Because due to these kind of fluctuating power generators, we need any kind of balancing power generators. So in these terms, in case that the cost of the solar and also wind can be reduced significantly, and they becomes the lowest price in our grid, actually, we can convert this kind of fluctuating and also surplus electricity to the hydrogens, and then utilize the hydrogen for any kind of premium market, which is utilized for a balancing market itself. So I think this kind of strategy, we need any kind of market reformations in our energy systems. Thank you very much.
Thank you, Professor Aziz. The next question is for Dr. Apip Amrullah. Which better, using biochar as fertilizer or carbonization for energy in terms for reduction GST emission? Please kindly, Dr. Amrullah.
Okay,
to give,
thank you very much for the nice question. Actually, in my opinion, that is best for on your purpose. If you want to use, if you want to reduce the GSSD emission, it should be better to making the for the fertilizer, right? Because there is no air pollution when we produce. However, if we want to reduce the in case of the economic value, for example, we can use as the combustion for the power plant, such as to mix with the coal for the power plant. So to making the solid fuel, for example, to make a pellet or something else, and then making mix or the blend with the coal. So it means that we can reduce the cost from the in case of the combustion the power plant. So it means that for based on the purpose, if you purpose to reduce the DSD, so it means that the fertilizer is better because there is the produce for the air pollution, right? And then if we concern about the economic, maybe it should be, for example, we can blend with the coal to the process in the power plant. So it means that making the some solid fuel such as pellet or something, and then blend it with the coal. So it means that's my answer. Yeah. And then the second one, I think there is the question from Dr. Lucy, right?
From Dr. Lucy, which type of biomass source will be environmentally and economically in the future, especially in Indonesia? And then so far, from your research experiences, which area is probably still unexplored in the field of bioenergy?
Okay, so if we concern about the environmental economically, it should be it's better to use the waste as actually the waste is such as biomass. So this means that there is no the cost can be used to produce some product from the waste, right? Actually, we know that the waste is kind of the biomass also. For example, that the food waste, the plastic waste, as mentioned from the Dr. Panji, actually there is this kind of the biomass also. So it means that if we think about the environmental economically, it should be better when we use the waste as the raw material. And then the second one is the what kind is not is not explored, right? As I mentioned before, that the for in case of the eucalyptus is more interesting to be focused on, because as we know that eucalyptus is kind of the short rotation plant. So it means that we can using all of the part from the eucalyptus to making some sources for the renewable energy in the future. This is my comment. Thank you.
Okay, nice explanation from Dr. Afif Abdullah. Okay, I think that's all the question from the chat box. Is there any question from audience? You can directly ask for our speakers by click raise hand button, and I will let you to deliver your question. Is there any question for participants? No. Okay, I think I have curiosity. Okay.
I have one more question for Dr. Panji in chat box.
Oh, in chat box. From Pak Dirga. Is that right?
Yes.
Oh yeah, sorry, I'm so sorry. From Dr. Dirga for Dr. Panji. Dr. Panji, are you still here?
Yes.
Yep. I'm sorry.
Yes, I'm listening.
Yeah,
However, I cannot read the chat box, so I don't know.
Yeah, this question for Dr. Panji from Dr. Dirga. What is the promising conversion technology for production solid fuel, maybe torrefaction or hydrothermal carbonization or without carbonization?
Yeah, thank you, Dr. Dirga. We are searching for the most efficient conversion pathway for the solid waste. However, the biggest problem with the solid waste is the mixture. So in that way, we have a mixture not just in the term of chemical composition, not just in the term of physical composition, but also in term of sizes, hardness, and so on and so on. That way, I was focusing on dry torrefaction previously. It's quite natural because we want to have higher heating value from the waste, but it requires to have uniform, how should I say, uniform waste in the same size, in the same density, in the same outer diameter. In that way, we can have a better dry torrefaction. So afterwards, I moved to the wet torrefaction, to the hydrothermal process, because we want to treat this mixed waste, wet waste. And by using hydrothermal, we believe that we don't need to dry. We don't need the energy to dry the waste to become carbonized. It can be processed in a wet condition. But it also doesn't. It's not a single solution for that kind of waste, because for hydrothermal, we're going to need to make a reactor that is quite capable of handling high temperature and also high pressure. So plenty of the workshop in Indonesia are still not capable of making it economically. So we still have the problem in that term. Now, so far, I believe that waste separation, waste management is the important key for us to treat the waste in our technology. So far, I believe there is no one size fit all solution for this municipal solid waste. It's quite different with the biomass waste, but for municipal solid waste, separation is a must. I think that's my. I hope that answer your question. Thank you.
Thank you, Dr. Panji. We have one question more for Dr. Panji. What are sustainable and eco-friendly approaches to converting the biodegradable fraction of municipal solid waste or MSW into bioenergy? Thank you, Dr. Panji. Please kindly give your insight.
Okay, sustainable and eco-friendly. That's two keywords that is difficult to answer. We usually take a look at the life cycle cost of each process, and we actually just published a research on the comparison between the open dumping landfill and also incineration and also composting and hydrothermal and pyrolysis process. In the term of process effectivity, actually incineration is the best and the worst. In the term of greenhouse gases, the open dumping is the worst. It's even much higher compared to the incineration. So I think if we can open our eyes on the effect of each waste processing to the environment. But we want to talk about the sustainability. That means we need to combine the three aspects of sustainability: economical, social, and also environmental. So usually people are thinking more to the environment part, but not so much for the social part. And the third one is for the economical part. This is the typical when people think how economic it is. So it's it's quite it's quite difficult to answer, but in my opinion, combustion or burning as fuel is the last option that we shall do for the residual waste, for the waste that can be converted into other form, into usable form, a form like, for example, for the form of organic fertilizer, for example, in the form of construction material, for example, and in other forms. I think the most sustainable thing to do is to use it as other material, and the last stage is to throw it away. No, the last stage is to burn it away. But the worst thing is to just throw it away without it. I hope that answers your question.
Okay, thank you, Dr. Panji. Is there any question, ladies and gentlemen? You can raise hand. Okay, Dr. Dirga.
Oh, I'm not present. I'm give applause.
Oh, okay. I'm sorry. Yeah, yeah. Is there any question from all? Okay. I have one question for all speakers. As we all know that our country, Indonesia, will have a new capital city in East Kalimantan. And then maybe for all speaker can give us a brief suggestion for research strategy of clean energy production in our new capital city to be located. Several speakers have mentioned some clean and renewable energy resources, and some speakers also mentioned many potential resources in Kalimantan Island. But we need also more strategy how to manage to harvesting clean energy and renewable energy. Please kindly give a brief suggestion for us, maybe from all speakers. Maybe for the first one, Professor Aziz can give your insight.
Okay, thank you very much. I think I have talked previously also related to this new capital Indonesia actually. Okay, as I mentioned previously, that we need really to measures to assess what is the characteristics and also potentials of energy resources in Kalimantan also. Things we cannot just copy paste the scenario from other area actually, especially some big cities or some capitals located in tropical area is also the number of these capitals is also limited. So it means that we cannot only copy the scenario which has been applied to other capitals around the world actually. So in this case, as I mentioned previously, that like the limitations for the like the weather conditions, temperatures, humidity, wind speed, or etc. I think we need also to reconsider this one, and also what kind of systems that we like to adopt in this case. That it really not only focuses on the city itself, but also the surrounding area. So when we are talking about the sustainability, it cannot be only focused on the certain point of the regions, but also it will be really correlated with the surrounding areas, especially in these terms that for the Kalimantan or Borneo itself actually. So how far we can connect and how far we can remapping all of the energy resources available in Kalimantan, and also we would like to have this kind of new capital city in Indonesia. I think it will be the role models of another cities. So any other city, maybe we can try to follow, or we can try to copy paste. Although the scale maybe will be quite smaller compared with the new capital, I think, in Kalimantan. Thank you very much.
Okay. Thank you for nice insight, Professor Aziz. Maybe the next we will hear from Dr. Hanif. We are neighbor, right?
Yes, thank you very much. First of all, congratulations to you for setting up a new capital city and close to us as well in Borneo. And which brings to my point. So if you look into the resources we have in Borneo itself, so mainly, especially gas is very prevalent in Borneo region. So we have Brunei, and we have Sarawak, Labuan, and also down in Kalimantan, also around the Southeast Asia, South China Sea region is where all the gases are produced. So this could make us into a powerhouse of gas producers. So it gives us advantage also, but we need to use this advantage and plan carefully. So not to just use it and produce more carbon dioxide, but to have to develop technologies to how to efficiently use this gas technologies for our use, for example, for hydrogen production, as well as you can see there's some hydro plant building in Sarawak as well. So if you work together just within this Borneo region, we could be the powerhouse of the whole Southeast Asia, really. Thank you very much.
Thank you, Dr. Hanif. Maybe the next one from Dr. Apip Abdullah. Universitas Lambung Mangkurat is in Kalimantan Island also. Yes.
Okay. Thank you. I think this is the same case with the Lambung Mangkurat University, right? In our university actually focus is working on the wetland biomass. Actually, because the characteristics of our land is more what would we say, that the acidic, right? So more the wet biomass, so it's more respectively to improve. However, if we're talking about the sustainability, actually, that we need to think about the technology. So we need to optimize the carbon conversion from the multiple sources for the biomass feedstock also, and then also it should be reduce the fossil fossil fuel for energy uses, and also increasing the renewable energy sources usage for daily operation. Then the last one should be to improving the sustainability, including for the minimize waste production by recycling or something, and wastewater, solid waste, and something else. So it means that if we focus on the only one case, for example, that the wetland biomass is not is the goal, but also we need to think about the technology and idea to how to improve the sustainability to get the good sustainability in the future. This is my suggestion. Okay. And then we can make the networking with the ULM or something else in the Kalimantan to make the good growth in the future. Thank you very much.
Yeah, sure. Thank you, Dr. Apip Abdullah. Okay, maybe the next one we can hear from Dr. Panji from the session for our sustainability development, especially for our new capital city. Dr. Panji?
Okay, yeah, thank you, Ms. Musharrafah. I think, in new and renewable energy research center, we think that maybe people would tend to use renewable energy as the main. It seems clean, it seems green, it seems sustainable, but we are concerning about the energy storage for such renewables, for example, for battery or other chemical storage. So here it will be a problem. So contradiction, I think we are focusing on the physical energy, the chemical energy storage. The main problem in Kalimantan is not with the energy resource itself. Like Dr. Apip said, that most of the energy resources in Asia are available in Kalimantan. We have coal, we have gas. In some older parts, we still have oil, but for the energy source in our new capital, future capital, as long as we have the Kalimantan super grid, any power plant will do, as long as the grid is active. So we tend to say that we think about our local available energy source rather than thinking about the new source, which is development. It will be more reliable for our capital, because I don't know the English word, but we need to maintain the kemandirian and also ketahanan of energy. Those two are important for the capital. I think it will be number one priority for us.
Okay. Thank you, Dr. Panji. Maybe the last one from our special guest, Prof. Enomai, please kindly give us your suggestion, your insight for our new capital, Indonesia, new capital city in Kalimantan or Borneo Island for sustainable development in energy. Prof. Enomai, are you still with us?
Yes, still connected.
Yeah.
So I don't understand well the question.
Yeah, Prof. Enomai, Indonesia will have a new capital city in Kalimantan Island. So please give us a suggestion from how to manage our resources to achieve sustainable development in energy.
So my suggestion is that to build a city. So first make a plan, and for sustainable development, like low energy consumption and utilization of the renewable energy. And in Japan, Japanese government asked each local government for a declaration of zero carbon city. The many, of course, finally, almost all the cities and the prefectures have to declare the zero carbon declaration. So, and then each local government have to think about what kind of measures should be taken to for sustainable development. And then, so in Kalimantan also, there are several cities, and they propose their own idea for sustainable development, and summarize, and the combination of all the projects will be a poetry sustainable society of Kalimantan. So separation and then finally united plan is important, I think. This is my suggestion.
Thank you, Professor Enomai. Okay, for all participants, is there any more question for our speakers?
Yeah, I think the time is over.
Okay. Yeah. Thank you, Dr. Lucy. Yeah. Time
So
is
now,
up. Yeah. Time is up. Finally, that's all for today, ladies and gentlemen. On behalf of moderator, thank you for everyone joining us today and participating in the webinar. I hope our knowledge has been expanded by this meeting, and I hope also this webinar provokes the future meaningful collaboration between our institution. I will give it back to MC, Bu Asmia. Time is yours.
Okay, thank you, Dr. Musharrafah. Lastly, I would like to say thank you to Dr. Musharrafah for leading the presentation and discussion session. And now I would like to say thank you for all the speakers for the great insight related to renewable energy. And I will share the online certificate of all presenter for today. The first one, I would like to award the certificate to Professor Toshiharu Enomai. Thank you, Professor Enomai.
Thank you.
And the next one is for Dr. Abdul Hanif Mahadi. Thank you, Dr. Hanif. And the third one is for Dr. Eng Apip Amrullah STM Eng. Thank you, Dr. Apip. And the next one is for Associate Professor Muhammad Aziz. Thank you, Professor Aziz. And the last one is for Dr. Eng Panji Prawisuda STMT. Thank you, Dr. Panji. And once again, I would say thank you for all the speakers for sharing their knowledge with us. And thank you for all the participants who have participated until the end of this session. We have spent almost 3 hours together to hear some insight about renewable energy. And I would kindly remind to all of the participants to fill the presence form, and you will get the participant certificate sent directly to your email. And lastly, I would like to apologize if there are any mistakes during the event. And see you on the next event. Wassalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. Thank you for
Terima
all.
kasih
Thank you, Enomai Sensei. Thank you for all participants.
Thank you. Terima kasih.
Terima kasih Prof.
Terima
Enomai.
kasih. Terima kasih.
Otsukare sama desu, Sensei.
Hai, otsukare sama.
Des.
I see you again.
Arigato.